Invite the speakers and participants, all of you, for the first session of today, which is the last day of our conference. And Shubho Roy from IIT Hyderabad, right? Sorry, it is IIT Hyderabad will be taking charge of today's session now. So Shubho, it's over to you now.
Thank you very much, Ryan. So a very warm welcome to everybody on this final day of the talks. So we have a very interesting session today. The first speaker is Thomas Rudelius from the, so he's not now at the Institute of Advanced Studies, he's moved to UC Berkeley. And he's going to tell us about the landscape of swampland conjectures. Please, the duration of the talk is 45 minutes, and then we have 15 minutes for questions. So if you have short questions, please feel free to interrupt. If the question you feel a bit longer, you can postpone for the question session at the end of the talk. So please, Tom, you can begin.
Great, thank you very much for the invitation and the introduction. And since the audience is rather small right now, I think anyone should just feel free to interrupt with any questions that you may have. So my talk today is going to be indeed on the landscape of swampland conjectures, and it will be primarily based on some work to appear with Clay Cordova, Kantaro Omori, these authors here, as well as a paper that's already out with Shuheng Xiao. So a quick outline. I'm going to start out by talking about the landscape in the swampland. I'm going to then talk about higher form global symmetries and tie these ideas together in several different ways. And finally, I'll end with some conclusions. So to begin, the big picture is that string theory does not seem to give rise to a unique low energy effective field theory, but rather a vast landscape of effective field theories, which could have ostensibly described our universe. Now, whether you think this landscape is a good thing or a bad thing in large part depends on your perspective, but certainly from the perspective of testing string theory experimentally, the landscape presents a bit of a headache. Simply put, the more possibilities you have, the harder it is to make a unique prediction. From this perspective, there is some welcome news, which is that although the string landscape seems to be very large, it's likely only a small part of an even larger swampland of effective field theories, which have the property that although they may seem consistent as low energy effective field theories, if you try to couple them to quantum gravity and complete them in the ultraviolet, you'll find that it simply cannot be done. So the goal of the whole swampland program, as it's sometimes called, is to try to delineate the boundary between these two, to figure out what exactly are the universal features of quantum gravity theories in the landscape, which distinguish them from the sick effective field theories in the swampland. And ideally, what we'd really like to be able to do is to take these universal features and to derive some low energy consequences from them, something that we can actually go out and measure, effectively amounting to low energy consequences of high energy quantum gravity physics. Now, in practice, this whole program is actually quite complicated. Quantum gravity, it turns out, isn't so simple. The way that the whole swampland program has taken shape in practice is that people have come up with a number of different swampland conjectures, and other people have then tried to take these conjectures and put them to the test, either finding further evidence in their favor, in some cases finding counterexamples to the conjectures. Now, Kamran spoke a couple days ago on a number of these conjectures, and in fact, he mentioned more of them than I will discuss in my talk. Here are just a few of these conjectures. And there is, unfortunately, a little bit of a trade-off in general when it comes to these conjectures. Some of them tend to have more evidence in their favor. They tend to be more rigorously established. But those conjectures tend to also have less interesting phenomenological consequences. And conversely, the conjectures that have more interesting phenomenological consequences tend to have less evidence in their favor. So of course, where we'd really like to be is up here in this upper right-hand corner, where we have conjectures that are both rigorously established, as well as lead to interesting phenomenological implications. And sort of the entire point, the sort of the goal of the swampland program is to try to push ourselves into this upper right-hand corner. Now, these various conjectures have a number of different relations between them. So here are just a few, a small sampling of the conjectures I mentioned. And you see that just by simple things like electromagnetic duality, Kaluza-Klein reduction, this idea of emergence, in which weakly coupled low energy physics emerges from strongly coupled quantum gravity dynamics at the Planck scale, leads to a number of these different conjectures. My goal for today is to sort of introduce some new links into this web of swampland conjectures. And in fact, many of these links were actually discussed by Kamran Bafa in his talk a few days ago. In fact, to be honest, much of what I planned to say in my talk was sort of previously said by Kamran. Many of the different conjectures and the relationships between them were summarized very nicely in his talk. So what I want to do in this talk is to go into a little bit more detail. So Kamran sort of gave a little bit of the lay of the land, but what I want to do today is to explain in a little bit more detail how exactly it is that the statement of no global symmetries in quantum gravity has such wide-ranging consequences for all of these other swampland conjectures. So with that, let me now get to the idea of higher form global symmetries, which are going to play a starring role in my talk today. Higher form global symmetries were introduced to the quantum field theory world by these authors here in their seminal 2014 paper, and have since taken the quantum field theory world by storm. The idea behind a higher form global symmetry is that it's going to generalize the notion of an ordinary global symmetry, where instead of charged local operators, we have charged operators that are supported on manifolds of dimension greater than 0. So a Q-form global symmetry has charged operators which live on manifolds of dimension Q. In the case of an ordinary global symmetry that we know and love from quantum field theory classes would correspond to the case of Q equals 0, as the charged operators live on points in space-time. Global symmetries are associated with a group, G, which may be either discrete or continuous. Ordinary global symmetries may be either non-abelian or abelian, but higher form global symmetries are necessarily abelian. If G is continuous, then under some reasonable assumptions, there is a conserved D minus Q minus 1 form Noether current, which is closed. So D of J is equal to 0, and that's the statement that this Noether current is conserved. For anyone who's not so familiar with the language of differential forms, the statement that J is a D minus Q minus 1 form means that we can integrate it over manifolds of dimension D minus Q minus 1. And we will see examples of that shortly. Symmetry transformations in this modern view of quantum field theory are implemented by these operators, which are known as symmetry generators or sometimes as charge operators. Each such operator is associated with an element of the group, as well as a manifold of dimension D minus Q minus 1. And these operators satisfy a fusion law. If I fuse two of them, labeled by G and G prime, living on the same manifold M, I get a third operator labeled by G double prime, where here the fusion proceeds according to the group multiplication law. G times G prime equals G double prime. These operators are topological. And by topological here, I mean that an operator that lives on some manifold M is equal to the operator on some other manifold M prime, provided that we only consider smooth deformations between M and M prime, and we don't cross over any charged operators in the process. So these operators are equal to each other in the sense that any observable or any correlation function involving one of these operators is equal to the same correlation function with the other operator. For the case of a U1 global symmetry, we can be a little bit more precise about the form of these operators, namely an operator U labeled by this group element e to the I alpha and some manifold M is given by the exponentiated integral of the Noether current over this manifold of dimension D minus Q minus 1, where alpha here labels the phase. Symmetries are associated with word identities. And in the language of these charged operators, the statement of the word identity is that if I surround one of these charged operators with one of these symmetry generators, this is equal to the charged operator I started with times a representation of the group, which in the case of U1 or some abelian group is just a phase. Pictorially, what we're doing here is we're surrounding one of these charged operators with this symmetry generator. Because this thing is topological, we can shrink it to 0 size without affecting any correlation function. And if we shrink it all the way to a point, we get back the charged operator we start with times this phase. So let's see an example to see how this works. Sort of the prototypical example of a higher form global symmetry comes in abelian gauge theory. So we have a U1 gauge field. The kinetic term looks like this. This theory actually has not only one, but two one-form global symmetries, each of which is a U1 global symmetry, an electric one, and a magnetic one. The other currents are given respectively by star F up to these constants and F. And the statement that these other currents are conserved follows from Maxwell's equations. In the absence of electrically charged particles, D star F equals 0, and in the absence of magnetic monopoles, dF equals 0. The charged operators live on manifolds of dimension 1 because these are one-form global symmetries, and in fact, they're nothing but the Wilson lines and the 't Hooft lines of the theory, respectively. The word identity looks like this. I take a Wilson line. I surround it by one of these symmetry generators, which is again given by the exponentiated integral of the other current. I can shrink this to 0 size. I get back the Wilson line I started with times this phase, which depends on the charge of the Wilson line and alpha, the element of the group. Now, what happens if we add in some fermion into the story? So some charged particle. It could be a scalar, it could be a fermion. It's just some charged particle, say of charge n. Well, something you can see immediately is that this charged particle is going to break explicitly the one-form electric symmetry. Because you see, D of star F is no longer equal to 0. So this other current is no longer closed in the presence of the fermion. Now, another way to see this, actually, as I'll mention in a minute, is that in the presence of the charge n fermion, the Wilson line of charge n can end. So rather than being some closed loop, this Wilson line can now have an endpoint, which is a local excitation of this field psi. And as you can see here, this is important because it means that we can unlink the symmetry generator from the Wilson line. And this allows us to consider the following thought experiment. So suppose we have some Wilson line of charge n, which ends on this fermion of charge n, and we surround it with one of these symmetry generators. Now we can compute this correlation function in two different ways. The first way is to just shrink this thing to a point. If we assume that the symmetry generator is topological, we can shrink it to a point, and the word identity tells us that we'll pick up this factor of e to the I alpha n. On the other hand, we can also unlink it from the Wilson line. We can slide it down here, we can shrink it to 0 size, and now the word identity says that we should just get a trivial phase factor. So if we equate these two on the left and right, we find that under the assumption that this operator is topological, we must have e to the I alpha n equals 1, which in other words means that e to the I alpha is an nth root of unity. In other words, in the presence of the charge n fermion, it's no longer true that every alpha gives rise to a topological operator. The only alphas that do give rise to a topological operator, U, are those which are nth roots of unity. In other words, the U1 global symmetry has been explicitly broken by the addition of the charge n fermion down to a Zn subgroup. Now, symmetry breaking is important in quantum gravity because quantum gravity theories are believed to not have any global symmetries. The original argument from which sort of follows from some of Hawking's work in the 80s and was nicely summarized by Banks and Seiberg in their 2010 paper, deals with the case of just ordinary global symmetries. But there are reasons to believe, including a recent paper of Harlow and Oguri, that in fact, quantum gravity shouldn't have higher form global symmetries either. And so sort of the generally believed statement of global symmetries in quantum gravity, at least the one argued for in this paper, by Harlow Oguri in the context of ADS-CFT, would say that you cannot have a p-form global symmetry in a quantum gravity theory in d dimensions whenever p is less than d minus 2. So this would rule out an ordinary global symmetry in 3 or more dimensions. It would rule out a 1-form global symmetry in 4 or more dimensions, a 2-form global symmetry in 5 or more dimensions, etc. Okay, so now we have this background on higher form global symmetries. I've talked to you about this one Swampland conjecture, which is that quantum gravity shouldn't have such higher form global symmetries, at least not in appropriate dimension. What I want to do now is to talk about how that particular Swampland statement can be related to a number of other Swampland conjectures that have been discussed. And the first one I want to talk about is the completeness hypothesis. So the completeness hypothesis, also known as the statement of completeness of spectrum, is a statement that in some d-dimensional gauge theory with gauge group G in quantum gravity, there should exist states, that is to say particles or multi-particle states, in every representation of the gauge group G. And it's often noted that this is related to the absence of global symmetries. So why is this? Why is this related to the absence of, in particular, higher form global symmetries? Well, we can see why just by considering the simple U1 gauge theory example that we discussed previously. We saw that when we have pure U1 gauge theory, we have this electric one-form global symmetry with group U1. And we saw that if we added in a particle, some state of charge n, which would, upon taking multi-particle states, would give us states of charge n, 2n, 3n, and so on, this breaks the one-form global symmetry from U1 down to Zn. It follows then that if we have states of every charge, so if you have a particle of charge 1, and then another state of charge 2, 3, 4, etc., this is going to entirely break this electric one-form global symmetry, and there will be no remaining electric one-form global symmetry. So at least in this U1 example, you see there's this perfect one-to-one relationship between satisfying the completeness hypothesis, having states of every charge, and the absence of any electric one-form global symmetry. So the absence of one-form global symmetries is intimately related to the completeness hypothesis in this example. And you might think that this is a more general phenomenon, but in fact, this is not. So for S3 gauge theory, for instance, even if there are no charged particles, so you have no matter in any representation of this group, you will still find that there is no one-form electric global symmetry. So naively, this seems to be a counterexample to this relationship between the absence of global symmetries and the completeness hypothesis. However, there's a more general statement in this theory, which is true. Although there are no codimension 2 topological operators associated with a global symmetry, a one-form global symmetry, there are more general topological codimension 2 operators. So what do I mean by this? You remember that a one-form global symmetry is associated with these topological codimension 2 operators that fuse according to the group multiplication law. But a more general topological operator will have a more complicated fusion algebra. Rather than fusing 2 of these more general operators to get a third one, you'll fuse 2 of these and get a sum over topological operators. So indeed, the completeness of the S3 gauge theory is not related to the absence of one-form global symmetries, but it is related to the absence of these more general codimension 2 topological operators. And so this is actually pointing us to a more general statement. In the case of a compact connected Lie group, like U1 or SUN, like SU3 times SU2 times U1, or most of the examples that we're familiar with in usual studies of quantum field theory, completeness of the spectrum is indeed equivalent to the absence of these one-form electric global symmetries. This is also true for a finite abelian group like Zn. But for a more general compact disconnected Lie group, like for instance O2, or a finite non-abelian group like the S3 example we just saw, completeness of the spectrum is instead equivalent to the absence of these more general topological codimension 2 operators, which are also known as Gukov-Witten operators. So this statement here generalizes this statement here, and it actually leads us to a further generalization, which is that if you don't believe that codimension p+1 symmetry operators, symmetry generators, should exist in dimension d for d p less than d minus 2, it's natural to think that these more general topological operators also should not exist. So what we see is that the statement of no global symmetries in quantum gravity is actually just a particular example of this more general conjecture, that there should be no topological operators in a consistent theory of quantum gravity, specifically of this codimension. The argument against global symmetries given by Harlow and Oguri in ADS-CFT actually doesn't generalize so nicely to these topological operators, nor is it obvious that the argument of Banks and Seiberg generalizes. So it remains an open question to put this conjecture on more solid footing. But it is a very natural conjecture of a statement that we've already seen. So what do we have so far? We've seen that no topological operators is a natural generalization of the statement of no global symmetries in quantum gravity, and it immediately implies the statement of the completeness hypothesis. Next, I want to talk a little bit about Chern-Weil global symmetries. Chern-Weil global symmetries are defined, for the purposes of my talk, to be symmetries whose conserved currents look like this. In a gauge theory with gauge group G, say U1 or SUN or something like this, we get a whole family of conserved currents for any integer k, whose which are given by the trace of f wedge f k times. The conservation of these currents follows in the abelian case from simply df equals 0, the Bianchi identity, as well as the non-abelian Bianchi identity for G non-abelian. So as a result, the conservation of these currents is a rather general phenomenon, and they aren't so easy to break. Now, strictly speaking, if this is a two-form gauge field, then one of these currents is a 2K form. And so this is going to generate a global symmetry provided that 2K is less than the dimensionality of space-time. There's sort of a degenerate case where 2K is exactly equal to the dimension of space-time. This happens, for instance, in 4 dimensions. We can consider the case of k equals 2. So trace of f squared is a 4 form. It's a top form in 4 dimensions, and therefore it's trivially conserved. So d of j is equal to 0 trivially. Nonetheless, there's sort of a sense in which you could think of this thing as generating a -1 form global symmetry, for which the associated charge is instanton number. So you have to be a little bit careful with this because, as I say, it's sort of a degenerate case, but nonetheless, it will be sort of useful to have this in mind, and we'll revisit this degenerate case in a few slides. So as I said, sorry, let me go back. These global symmetries are not so easy to break. And yet, in quantum gravity, we believe that there cannot be exact global symmetries. So these things must be removed somehow. And there's 2 ways to remove a global symmetry in an effective field theory. We can either break it or we can gauge it. So over the course of the case of these Chern-Weil global symmetries, you can consider some examples of each. For an abelian symmetry, the simplest way to break it is simply to add monopoles. So in the presence of monopoles, df is no longer equal to 0, and therefore d of f wedge f is no longer equal to 0. And the symmetry is broken by the addition of these monopoles. On the other hand, instead of breaking the symmetry, you could also gauge it by coupling this Chern-Weil current to a d-4 form gauge field. The equation of motion for this gauge field is then going to give you something that looks like this. F wedge f is equal to d of something. And in other words, what this is telling you is that f wedge f is an exact form. And exactness of a form is sort of a hallmark of a gauge symmetry. So by coupling the current to a gauge field, we render the current exact and we render the symmetry gauged. And this is good because there's nothing wrong with gauge symmetries in quantum gravity, but we aren't allowed to have exact global symmetries in quantum gravity. So we've seen one example now of breaking and gauging. The example of breaking that we just saw was specifically for the case of an abelian Chern-Weig current, but we can also consider examples where non-abelian Chern-Weig currents are broken. And perhaps the cleanest way to do this is via grand unified theory symmetry breaking. So let's suppose we start out in the ultraviolet with an SU5 gauge group, and we break it down to SU3 times SU2 times U1. In the ultraviolet, we have a single Chern-Weig current, namely trace of F squared, where the gauge group is SU5. And this is gauged in D dimensions, where here you should, for concreteness, think that we're working sort of in D greater than 4. This is gauged by some D minus 4 form. So this gauging will remove the one Chern-Weig current, and it doesn't leave us with any remaining Chern-Weig currents. But if you go to the IR, now it looks like we have 3 Chern-Weig currents, an SU3 squared, an SU2 squared, and a U1 squared. That means that if you're an IR effective field theorist, you would expect that there should be 3 Chern-Weig currents. But the ultraviolet field theorist knows that in fact there's only one which is gauged. So what actually happens is that the other 2 linear combinations that are not gauged in the ultraviolet are actually going to be broken in the ultraviolet by the unification process. So these things look like perfectly valid symmetries in the infrared. The conservation of these currents follows again from just the Bianchi identity. But when you get to the ultraviolet, you realize that in fact these things are broken and the 3 gauge groups unify into a single one. So what we see now is that this unification, in fact, serves as another way to break these Chern-Weig symmetries. Now, what does this have to, why are we interested in this? So I want to argue now that these Chern-Weig currents actually lead to some interesting consequences, in particular for axions in quantum gravity. So in string theory and in string compactifications, axions are ubiquitous. These are can be thought of as zero-form gauge fields. They're compact scalar fields, and they show up all the time in string compactifications. Now, there's a reason why this is from the Chern-Weig perspective. From the Chern-Weig perspective, we know that whenever we have some gauge field in some d-dimensional theory, we're going to get these Chern-Weig currents, and generically, we expect that at least some of them will need to be gauged. And this is accomplished by coupling them, as we just saw, to this d-4 form gauge field. Now, what happens if you start with a term like this in greater than 4 dimensions, and you compactify down to 4 dimensions, is that this term is going to reduce to a term that looks like this. Theta trace of F wedge F, where this theta here is an axion. So axions, we see, are playing the role of gauging these Chern-Weig currents. And therefore, the demand that we don't have global symmetries in quantum gravity leads us to expect that some of these currents at least will be gauged, and therefore it leads us to expect the existence of axions. So in other words, the Chern-Weig perspective helps us to explain why axions seem to be so ubiquitous in string compactifications. We aren't simply looking under the lamppost, but rather axions are intimately related to the statement of no global symmetries in quantum gravity. Another interesting consequence of these, the breaking of Chern-Weig currents is the implication for the so-called axion quality problem. So in QCD, we solve the axion, solve the strong CP problem using an axion whose potential looks like this. We have some dynamically generated scale. We have this e to the minus s. We have some UV scale, and we get some dynamically generated scale, which includes this factor of e to the minus s QCD. And crucially, this potential is going to have a minimum at theta equals 0, so that this field will relax down to the minimum. And the axion quality problem is the problem that if you have some other term that looks like this, which has a minimum, which is not at the origin, but rather is shifted by some phase delta, then if this term dominates over this term, the minimum of the potential will not be at 0, but rather near this parameter delta, and therefore we will violate and we will spoil the solution to the strong CP problem. So if delta is not equal to 0, you need this S other to be much larger than SQCD. And a priori, you might wonder why on earth we should expect such a thing to occur. Now, the Chern-Weyl perspective doesn't completely resolve this problem, but it could ameliorate it somewhat for the following reason. If we have two different types of instantons, say two different gauge groups in our theory, QCD and some other, so SU3 as well as some other gauge group, you might naively expect that the axion theta will couple to both. But the Chern-Weyl perspective says that, in fact, if we have these two different gauge groups, then either both of them need to have their Chern-Weyl currents gauged, in which case you would expect two different axions coupling respectively to the different gauge groups, in which case this sort of problem doesn't arise. Or if you just have the single axion which couples to both, then one of the Chern-Weyl currents is going to be broken. And as we just saw, sort of the main way that this occurs is by this process of unification. So we would expect that if the same axion theta couples to both of them, then in some sense these two theories, or in some way in the ultraviolet, these two theories are going to unify into a single gauge group. And this means that the physics which gives rise to these two different terms is not going to be completely independent of one another. We only need to worry about gauge sectors that can be unified with QCD. And so this may give us sort of some reason to believe that these problematic terms aren't going to arise because the physics of these two terms is correlated in some way. So we see that this absence of global symmetries implies the absence in particular of these Chern-Weyl global symmetries, which is related to even the existence of axions, as well as the axion quality problem in the ways we just saw. Now, finally, I want to talk a little bit about approximate global symmetries. We've seen that exact global symmetries in quantum gravity lead to exactly topological charge operators. We haven't talked about approximate global symmetries, but from what we have said, you can sort of imagine what we mean by an approximate global symmetry. It's going to be something for which we have these charge operators, which are almost topological. In other words, they have only slight sensitivity to the manifold on which they're supported. And perhaps an easier way to think about this is that the current will be almost conserved. So instead of d of j equal to 0, we'll have dj equal to some small number. Now, I want to make a swampland proposal that I'm going to try to justify in a moment, which is that not only should we not have exact global symmetries in quantum gravity, but in fact, all approximate global symmetries should be broken at an energy scale, which is at or below the Planck scale, or more accurately, at or below the energy scale at which gravity becomes strongly coupled. Now, why should we believe that something like this is true? The argument from Banks and Seiberg, based on ideas of Hawking, is that an exact global symmetry would lead to exactly stable black hole remnants at the Planck scale, which have been argued to be problematic for a number of different reasons. If you think that exactly stable black hole remnants are a problem, you might also believe that long-lived black hole resonances are a problem as well. And these are what you get if you have a global symmetry which is too good. So at the least, this leads you to think that maybe you shouldn't be able to have an arbitrarily good approximate global symmetry. Furthermore, this idea of approximate global symmetry breaking at the Planck scale matches our intuition, at least in simple cases. So for the case of, say, a complex scalar field, we expect that quantum gravity will give us some Planck-suppressed higher dimension operators, like this symmetry breaking term here. and demanding that the rotational symmetry of this scalar field phi is broken below the Planck scale is precisely the statement that this energy scale lambda should be smaller than m Planck. So here, the expected Planck suppressed operators indeed badly break this global symmetry where we would expect them to at the Planck scale.
Tom, can I interrupt?
Sure.
Just a question. If the gut scale is the Planck scale, will that be a problem for standard model then? Should it belong to the Swampland?
Well, so the gut scale. You're saying, for the case of like the Chern-Weil?
Yeah, exactly.
Oh, good. Okay, yeah, that's a good question. Yeah, so what you'd want to say here is that the gut scale should be sort of at or below the Planck scale. And in fact, more generally, what you want to say here is that in a sense, all weakly coupled gauge theories should become strongly coupled at or below the Planck scale, so as to avoid any approximate global symmetries at the Planck scale.
Yeah, but you said it is, I didn't get you. So you said it has to be below the Planck scale? That is making a stronger argument now?
Sorry. You'll note that there's this squiggle here. So all of my statements sort of from here on out are going to involve order 1 factors, which I'm ignoring. So when I say below Planck scale, I mean, somewhere around the Planck scale. The point is that you can't have a symmetry which is parametrically good by the time you get to the Planck scale. So at m Planck or slightly below, I guess I should really have written at or below here.
Thanks.
Yeah. Okay, so finally, the other reason why you might think that something like this should be true, and maybe the most compelling reason, is that it leads to agreement with a number of other swampland conjectures, which we tend to believe. So let me introduce you now to sort of the final stars of the show tonight. The first one is the weak gravity conjecture, which is really the most well-studied swampland conjecture over the last few years. It's the statement that in any d-dimensional U1 gauge theory, there must exist a super extremal particle in the sense that the charge of this particle divided by its mass is greater than or equal to the charge to mass ratio of an extremal black hole, which in Planck units is roughly equal to 1. And again, here I'm using squiggles throughout the rest of the talk. There's some order 1 prefactor here, which is known, but is not important for us. So pictorially, the weak gravity conjecture looks like this. If you plot charge on the x-axis and mass on the y-axis, the extremality bound is a linear relationship between the two. And the weak gravity conjecture says that you need a particle which is either on or below this line. So this particle here of this charge and this mass satisfies the weak gravity conjecture. Now, the weak gravity conjecture, the version I just stated is sort of the most mild version of the weak gravity conjecture. But for a number of reasons, people have become very interested in considering stronger versions of the conjecture as well. And one particular family of these conjectures, which has gotten the most attention and also has the most evidence in its favor, are the family of weak gravity conjectures known as the tower or sublattice versions, which Cameron actually mentioned briefly in his talk as well. And the idea behind these versions of the weak gravity conjecture is that it's not enough to just have a single particle on or below this line, but actually you need a whole tower of particles of increasing mass and increasing charge, which asymptote to this extremality bound here, like this. Now, what does this all have to do with global symmetry breaking? Let's go back to our old friend, this Lagrangian here. So we have a fermion, say of charge n, coupled to this Maxwell term. You remember that in the absence of this fermion, we have this conserved another current, but in the presence of the fermion, the current is no longer conserved as d of star f is no longer equal to 0. So it's interesting, though, to consider a couple of different limits of this Lagrangian. In the limit as g goes to 0, d of star f becomes equal to 0 as well. And indeed, the dynamics of the gauge field and the fermion field completely decouple. and we recover a one-form global symmetry. So for G very small, we have an approximate global symmetry. Similarly, if we take a limit as m goes to infinity, then if we're working at energies that are small compared to m, we will find that this fermion can be integrated out. The low energy consequences are exponentially tiny. And so to very good approximation, we find that d of star f is equal to 0. So that means that there are sort of these two different limits. Either G goes to 0, we get a one-form global symmetry, or M goes to infinity, we get a one-form global symmetry. And it's interesting because these are exactly the limits that the weak gravity conjecture is supposed to forbid. The weak gravity conjecture places a lower bound on the ratio of G to M in Planck units. And so we would expect that indeed to break this global symmetry at the Planck scale, we can't have G too small or M over M Planck too large. So it's really starting to smell an awful lot like the weak gravity conjecture. And indeed, with a more precise computation, which will appear shortly in this paper with Clay Cordova and Kantaro Omori, we will explain how this works a little bit more precisely using the language of these topological operators that we started with. And we'll see that in order to badly break this approximate one-form global symmetry requires the fermion in question to satisfy the weak gravity bound. This is the case for a single fermion, but more realistically, we would expect a whole collection of light particles. And what we will also show is that when you have a large number of particles, which together contribute to the breaking of this one-form global symmetry, what you find is that badly breaking this approximate global symmetry below the Planck scale requires us to satisfy this inequality here. In other words, in a sense, not just a single particle in the tower, but rather the average particle, the average light particle in the theory satisfies the weak gravity bound. And this is starting to sniff an awful lot like the tower and sublattice versions of the weak gravity conjecture. Indeed, in a theory which satisfies these conjectures, the tower and sublattice version, one can show that generically you will indeed badly break the one-form global symmetry precisely at the scale at which gravity becomes strongly coupled, at least up to order 1 factors. So there's this intimate relationship between badly breaking global symmetries, having no approximate global symmetries, and satisfying the tower and sublattice weak gravity conjecture. And this is especially important because these versions of the conjecture, in contrast to the ordinary weak gravity conjecture that we saw earlier, actually have some interesting things to say about phenomenology and cosmology model building. For instance, these conjectures say that it's generically very hard to get axion decay constants in quantum gravity, which are larger than the Planck scale, which agrees with other work that's been done looking into axion decay constants in string theory. And this is in particular very important because models of natural inflation in string theory tend to require axion decay constants which are larger than the Planck scale. And so those sorts of models are in tension with these conjectures. These conjectures would also say that the photon must be exactly massless. They place a lower bound on the mass of the photon, which is above current experimental constraints. It would also say that the QCD axion decay constant must be below the gut scale. And even more generally, what these conjectures would say is that there's some incompatibility between any theory which requires a very tiny coupling constant and any other theory which requires a very high energy scale. And this incompatibility gets worse as the rank of the gauge group increases. So for instance, here, this is for an SUN gauge group. You see that as n increases, sort of these bounds get tighter. And what these bounds are saying is that a model like chromonatural inflation, which requires a small coupling constant of order 10 to the minus 6, is going to be incompatible with, say, a grand unified theory or a large field model of inflation. Both of these will have energy scales that are too high to be compatible with both the tower and sublattice weak gravity conjecture, as well as a model with such a tiny coupling constant. So the tower and sublattice weak gravity conjecture are leading us to tension between some of these models that exist in the particle physics and cosmology literature. So what I've discussed now is the statement of no approximate global symmetries and how it implies the weak gravity conjecture and tower and sublattice weak gravity conjectures. Similar statements can be made to relate this conjecture to the axion weak gravity conjecture, the magnetic weak gravity conjecture, and the swampland distance conjecture, which I haven't discussed so much today, but which Kamran went into some detail on a few days ago. So in conclusion, let me wrap up. There are a number of relationships that we've now uncovered between appropriate generalizations of the statement of no global symmetries and many of these other swampland and quantum gravity features. So we saw originally that the absence of global symmetries is a special case of no topological operators, and we related that to the completeness hypothesis. We then saw that no global symmetries implied the absence of these Chern-Weig global symmetries in particular, which was related to the prevalence of axions in quantum gravity theories, as well as perhaps even the QCD axion quality problem. Finally, we saw that the absence of approximate global symmetries at the Planck scale led us to relationships with all of these different conjectures. This suggests a number of future lines of research. It would be nice to prove more rigorously that there are no topological operators in string theory or quantum gravity. It would be nice to develop a more precise statement of the no approximate global symmetries conjecture and to explain why it should be true, and to consider how it applies not only to continuous global symmetries, which is primarily what we've considered today, but also approximate global symmetries. Finally, I think it would be very interesting to apply it to other swampland conjectures, and perhaps even to other models in particle physics and cosmology. Thank you.
Okay, thanks very much for the fascinating talk, Tom. So we'd like to open up the session for questions. So Ashok had a question in the chat box. Ashok, you can go ahead and ask your question.
Okay, yeah. So my question was about the completeness conjecture. Does it refer to only single particle states, or does it include multi-particle states?
The completeness conjecture, as it's laid out, as it's been laid out, would also include multi-particle states and or bound states. Yes. So in particular, it's sufficient to just have a single particle of charge 1, and then you can consider multi-particle states to get everything else. Yeah.
I see. Okay. Thank you.
Yep.
So, are there any more questions from the audience? Please feel free. We have 10 minutes for questions. Okay, Tom, can I ask some stupid questions, couple of stupid questions?
Absolutely. There are no stupid questions.
I mean, I don't work in this field, so I'm not aware of this, but let me consider a concrete theory of quantum gravity, which is n equals 4 super Yang-Mills. It's a non-perturbably well-defined theory of quantum gravity. So I know there are global symmetries there because of the 6 scalars. So why is it that you state that in quantum gravity we cannot have global symmetries? Like, I mean, I should know the answer.
So you're talking about a global symmetry in the boundary CFT.
Yeah, but nonetheless, it is still the theory of quantum. I mean, non-perturbable. I mean, you know, the theory of quantum gravity, which is non-perturbably well defined. String theory.
Yes. And there's certainly no problem with having a global symmetry in the CFT description of a quantum gravity theory. The statement of no global symmetries is really dealing with the bulk spacetime. And in particular, in ADS CFT, what happens is that although you do certainly have global symmetries in the boundary theory, these are always necessarily gauged in the bulk space-time quantum gravity theory. So what you're saying is perfectly true, but it's not a counterexample to the no global symmetry statement, because we are really dealing with the bulk theory here.
So is the correct statement that there should be no global internal symmetries in space-time? Is that the statement?
As opposed to?
Because ADS 5 cross S5 has a global symmetry, which is the S5, you know.
Oh, sure. Yeah. Yes. That's right. Yeah.
And I had one more question. I'm not sure I followed that slide very well. So when you talked about this super extremal set of states You mentioned that that trajectory or that tower of states must merge with the extremality line. Can you tell me what is the intuition for that?
Yeah, let me go back to that slide. So actually, what I said isn't the idea that this tower should merge with the black hole spectrum here is not actually, strictly speaking, a stipulation of the conjecture, but it is a phenomenon which is observed in examples. And so, sort of the intuition, the logic that you should have, that you should understand this as, is that you have this tower of states, right, of increasing mass and increasing charge. And for small masses and small charges, we can think of these as being quantum mechanical particles in the effective field theory. Now, if we go very far out on the lattice, so very, very, very far out, well beyond the Planck scale, we still expect, according to these conjectures, to have such particles, if you will. Only now the term particle is a little bit of a misnomer because we expect these things to actually be black holes. And so down here, we expect to have these quantum mechanical particles, which are super extremal. Up here, we expect to have black holes. And you might say, well, how could a black hole be super extremal? Because we know that black holes, they have this extremality bound. But the point is that finite sized black holes receive subleading corrections to their charge to mass ratio. And in all examples that we've actually seen, these black holes have a charge which is just slightly larger. They have a charge to mass ratio which is just slightly larger than this. So they're slightly below this dashed blue line. And so that what we have is in examples, and this is what we actually see in string theory, both including in non-supersymmetric examples, like for instance, non-supersymmetric states in heterotic string theory. What we find is that at small charges, we have these super extremal particles. Up here at large charges, we have these slightly super extremal finite sized black holes. And the idea behind this conjecture is that sort of in some sense, there should be an interpolation so that actually throughout this entire region, throughout the entire charge lattice, we have these super extremal states. And in the middle, we don't know really whether to call them particles or black holes or something else, but sort of this tower exists everywhere. And so you should think that these states here are sort of asymptoting up to black holes in the large mass limit.
Okay, thank you very much.
Yeah.
Can I just follow up on that question? That if you really allow multi-particle states, then by combining black holes and the particles which are below, which are super extremal, can't you always produce such states?
Yeah, that's a good question. So, I mean, for this, if we were considering multi-particle states here, really, all we need is, all we would need is a single particle down here, and we can consider multi-particle states. So actually, this is sort of a tricky point. For the case of the completeness hypothesis, as it's usually formulated, the statement is just that we need some sort of states. They can be particles, they can be multi-particle states. For these conjectures, the tower and sublattice weak gravity conjectures, it's actually very important that these are not multi-particle states. They can be unstable resonances, which makes these conjectures somewhat ill-defined, especially when you don't have a weakly coupled gauge theory, so that so resonances might not be so long-lived. But when you have this weakly coupled gauge theory, you have these parametrically long-lived resonances. It's important that these things are single particle states. And there's a reason for that, actually. So the original argument from this paper of mine with Ben Heidenreich and Matt Rees for these sorts of versions of the conjecture deals with the case of dimensional reduction. And what we found is that you can actually dimensionally reduce a theory which satisfies the weak gravity conjecture and find a theory that does not satisfy the weak gravity conjecture after reduction. And that's not true with these versions of the conjecture, but that only works if you're dealing with single particle states as opposed to multi-particle states. So if you dimensionally reduce single particle states that satisfy the tower and sublattice weak gravity conjecture, you will still satisfy these versions of the conjecture after dimensional reduction. But if you just have a bunch of multi-particle states which satisfy these bounds, and you reduce that on a circle, you are not guaranteed to satisfy the weak gravity conjecture. So for these conjectures here in particular, Ashok, in contrast with the completeness hypothesis, it is actually important that we have are dealing with single particle states here.
Okay, thank you.
Yeah, thanks. Great question.
I have probably a clarification question, which might be quick. If not, we can go to Slack. So you were talking about a particular directionality that this no global symmetries implies WGC, but can one probably also turn it around? Or, for example, if I make some very naive argument like this in the context of Chern-Weil symmetries, an instanton doesn't carry energy momentum tensor. However, if you couple it to a dynamical axion, then it does carry energy momentum and it satisfies WGC. If I make this a reverse argument, what goes wrong?
Yeah. So indeed, I think you shouldn't take the directionality of these arrows too seriously. Really, what's true is that there seems to be some close relationship between this statement and these many other statements. And I think it's still too early to say sort of what is the most fundamental. And it's also not true that sort of it's not the case that no global symmetries immediately implies this statement. So we had to make some assumptions about how we have a number of light species, and these things contribute to the violation of this global symmetry at the Planck scale. And when we did that, we got up to order 1 factors these statements here. But there are assumptions that go into that, right? There could be other ways to break this global symmetry, perhaps, besides just by adding these tower of particles. So in a sense, what we have seen evidence for is some sort of relationship here, where, you know, if you have a theory which satisfies these conjectures, what you'll find is that global symmetries are badly broken below the Planck scale. So in some sense, our argument almost was even more starting from this. We find that this is satisfied, but I think it still remains the link here remains to be understood better. And it remains to be understood really what is sort of the deeper fundamental principle that underlies all of these swampland ideas. So I think what we've been able to do here is we've been able to partially motivate many of these ideas, and we've seen that there seems to be some sort of unification. There's some sort of web which underlies many of these ideas, and Kumran discussed that even more in his talk and talked about some other conjectures as well. But as to what is sort of the most fundamental swampland conjecture, or what the deepest reasons are for why these things seem to be related, I think definitely still remains to be understood.
Thank you.
Okay, thanks, Tom, for a very nice talk and answering all the questions. People who have follow-up questions can continue the discussion on the Slack forum. So we'll move on to our next talk, which is by Keshav Dasgupta from McGill University, and he's going to talk about constructing de Sitter space in string theory. Keshav, you can go ahead and share your screen.
Can you hear me now?
Yes, we can.
Okay, great. All right, I'm having difficulty sharing the screen. Let's see. All right. Can you see my screen?
Yeah, we can.
All right. So I thank the organizer for arranging such a interesting meeting, and I'm happy to talk a conference in honor of David Gross. So can you see when I move my cursor, does it go to the next page? It does, huh? Okay. So I'll start by saying that the search for de Sitter has become pretty intensive in the last couple of years, with debates ranging from absolutely yes to absolutely no with equal passion. And the neutral ones are the ones who are working with lambda less than 0 or lambda equal to 0 spaces. And but it will turn out that our answer will turn out to be yes. And we'll give a proof to justify our statement that de Sitter can indeed be found in the string landscape. Resolutely based on the following papers. These I wrote recently, and the last paper is the one which came a few years ago by Diwali and all, who actually came up with somewhat similar idea before us. But Diwali et al. Were doing this in 4-dimensional theory, and we try to do this thing in the full 10-dimensional theory. There are other relevant papers, which I will not directly talk so much about it, but they are also related to my work on the de Sitter space. So here is the cast of character. This is our postdoc, Shuddho, and this is Radu, with whom I wrote this recent couple of papers. And so let me just summarize some of my results. The thing I'll talk about is how to realize de Sitter space in the string landscape, and then discuss how to realize it as a Glauber-Sudarshan state instead of a vacuum. Then I'll say why it is a hard problem. And finally, I'll conclude by saying that although it's a hard problem, it still may be a doable problem. The question is how to realize de Sitter space in the string landscape. Now let us start by considering the following metric in the 4-dimensional de Sitter space, which is given in this particular form. And lambda is the cosmological constant, t is the time. And as many of you know, this is the metric in the flat slicing, which means that the time goes from -infinity to 0, which also means that the late time is given by t equal to 0. Okay, so this is my metric. So question is, how to realize this metric in string theory? For example, in type 2B string theory, how will I realize this metric? And our first conjecture would be that you put some warp factor in front of it, you put some warp factor in coupled with some 6-dimensional space, put the de Sitter space as the 4-dimensional space-time, and this could be a kind of metric that we would be looking for. It turns out that this metric GMN, which is the internal 6-dimensional space, is basically a non-Kähler space. It's not a Calabi-Yau space. Unfortunately, after much work, we found out that this metric actually is not good because of various reasons. And the metric that actually works appears to be the one with a similar thing in the 4-dimensional side, but the internal space picks up time dependencies. So here you see I've split the 6-dimensional space as a 4-dimensional times a 2-dimension with some time parameter f1t, a function of time, another f2t, and with the warp factor in this form. Now, the internal space is divided as M4 cross M2. It's not necessary, but it just simplifies our calculation. But this M and N belongs to M4 and alpha beta is M2. We also want to keep the 4-dimensional Newton constant time independent. So these coefficient that appears in front of the internal space, they satisfy this equation f1 f2 square equal to 1. Now our aim would be to show that this is a solution in string theory, and then realize it as a Glauber-Sudarshan state, and alternatively, which is also known as a coherent state. Now two questions arises. Why do we want to realize it as a coherent state in string theory? How can we realize this as a coherent state in string theory? Now, we'll start by showing that under what condition the 2B metric becomes a solution in string theory, and in the process, maybe the other question can be answered. Now, to realize this configuration in string theory, or as either as a solution or as a coherent state, we need various conditions. It turns out that we need explicit time-dependent degrees of freedom. Otherwise, such a configuration can be shown not to allow an effective field theory description in 4 dimensions. That is, it's in the Swampland. It turns out that there is no free vacuum in string theory, so our construction will specifically require an interacting vacuum. Such an interacting vacuum will have to be shifted by certain displacement operator to create the necessary coherent state. As you remember in quantum mechanics, how do we create coherent state? We take the vacuum and we shift it. But since there is no free vacuum, we have to search for interacting vacuum inside string theory and then try to shift it. It turned out that this provides some easy answers to very hard questions like entropy, vacuum energy, Transplanckian cosmic censorship, which is also known as TCC, etc. And that is, of course, why we want to construct it in an ultraviolet complete theory. Now, we have already raised too many questions here already. For example, why time-dependent degrees of freedom? Why coherent state at all? Why not just a vacuum configuration, as so far people have been saying de Sitter as a vacuum? Why interacting vacuum instead of free vacuum? Now, in the following, I'll try to answer at least some of these questions while motivating the others. And for computational efficiency, what I will do is I will lift this to M theory, where the metric takes this particular form. So I just take the type 2B configuration and lift this to M theory. Note that we have all degrees of freedom are the same, and the M theory lift is just for efficiency in computation. There is no particular reason of choosing M theory. Could have done in 2B, but M theory turns out to be much easier to handle. Note, this GS is the type 2A string coupling. And this type 2A string coupling takes this particular form, which is unfortunately time dependent. Z over here, which appears, is this toroidal direction, is the coordinate of the toroidal. It takes one of the x3 and x11, you combine it to form a toroidal direction like that. Now, this has already started bad with time-dependent type 2A coupling. We never encountered such situation before, because we never studied time-dependent solution in string theory. And you'll see why it is such a hard problem. But the worst is still to come. For example, in M theory as well and in dual type 2B is time-dependent. The type 2A coupling is also time-dependent. So the fluxes supporting such a background should also become time-dependent. Now, such a time-dependent configuration should solve some equation of motions. Question is equation of motions of what? Now, clearly, as shown in our 2014 paper, no classical sources can give rise to the above background. That means if you add fluxes, branes, anti-brane, orientifold planes, or any mixture of all of the above, you can show that you can never get a solution of the kind that we want. In other words, it's impossible to get a de Sitter solution with any of the classical sources. There have been some papers saying that de Sitters can be got by orientifold planes and all. I don't think those solve the equation of motion. None of them actually solve. They're either completely unstable or they don't solve the equation of motion. So no classical sources can ever give rise to a de Sitter vacuum. So how are we realize such a background? Now, we also know that string theory is not supergravity. So realizing such a background as a solution to some equation motion is tricky. But we know that we are also in energy scale much smaller than M Planck or MS. Plus, we want to realize it the background at late time. Now, as I said before, late time means that we take time t going to 0. Interestingly, this is also a weak coupling limit in the type 2A side. You see G string is proportional to T. That means T going to 0 is small type 2A G string. This is despite the fact that the coupling itself is changing with respect to time. So here is a very bizarre situation. We have a type 2A theory whose coupling is changing with respect to time. But T going to 0 is weakly coupled. So we can ask, what is the regime of time under which the theory remains weakly coupled? And you can easily show that if you are in the time limit -1 over square root of lambda and 0, we are at weak coupling. And many people who have been working on the field must have noticed that this is also the bound set up by Transplanckian cosmic censorship. So we automatically get all the bounds set up by TCC. So if you are in this time limit, we will always be weakly coupled, despite the fact that the coupling constant is varying with respect to time. So we'll try to remain inside this limit. And fortunately, since TCC says that if you are inside that particular limit, you are good. So we see that these two facts seems to coincide, and this looks like a silver lining in the dark clouds. So we are at weak coupling, and the energy scales are pretty smaller than M Planck. So maybe then we can write the following, that Rmn minus half Gmnr equals to the energy momentum tensor from all the classical sources, energy momentum tensor from all the quantum. We could write that equation because we are at weak coupling, energy scale is smaller than M Planck, where, as I said, Tmn classical is the energy momentum tensor for the classical, and Tmn quantum is the energy momentum tensor for quantum terms. M and N are all the 11-dimensional coordinates. Now, what are the energy momentum tensor from the classical? There can be energy momentum tensor from fluxes, can be branes, can be anti-branes, can be O-planes. What is the energy momentum tensor from quantum? It could be energy momentum tensor from all the possible perturbative correction in the theory, all the possible non-perturbative correction from the theory, all the possible non-local counter term from the theory, all possible topological term from the theory. Of course, by O-planes, we mean the M theory lift of O-planes, because there is no orientifold plane as such in M theory, but we know that O-plane can be lifted in M theory. Now, as I said, TMN classical is actually completely useless to generate a background of the kind we want, even in the presence of O-plane. So the only saving thing would be the energy momentum tensor from the quantum piece. Unfortunately, here comes the first problem. We have no idea what are all the perturbative, non-perturbative, and topological quantum terms, as well as the non-local counter terms in M theory. So this is sad. So question is, how are we to proceed? One way out would be to take everything that comes to mind, that is every possible coupling that may be allowed in a Wilsonian effective action. Take everything, whatever comes to mind. You could say that it will then be impossible to solve the system. Or maybe some of you might ask, how do we even know that Wilsonian method of integrating out high energy modes work when the modes are themselves changing with respect to time? See, de Sitter or a time-dependent background is something very bizarre. We never encountered such thing. If you try to quantize it, you will find that the modes are themselves changing with respect to time, which means that the Wilsonian method that we know and love does not work in this particular way. I mean, if you try to integrate out high energy mode, those mode, if you wait a little bit longer, become low energy. So you don't know exactly how this Wilsonian method would work. So this later question about the Wilsonian will come back if time permits. But for the first question, let's see what we can do. Now, in view of time, we'll only talk about the perturbative terms, and the other terms I will just motivate. And they have been discussed in our paper. Now, they are literally an infinite possible perturbative interaction we could think about. But this is not good. But also, if we take complex instanton into account, maybe the infinite non-perturbative terms could be summed as a resurgent trans series by performing Borel summation. That could also come about. Now, this is already getting harder. So let's push and see where we go, at least with the perturbative term. So question is, assuming that this is the way to go, what are the allowed perturbative terms at small g string and low energy? Okay, how about this? We take all possible flux terms, all possible curvature terms, all possible derivatives, raise them to arbitrary powers, and then sum them all up. Something like the following. So here I have collected all possible curvature terms allowed in this background. Ignoring, of course, you should also take into account their permutation. So there are approximately 27 possible choices of curvature terms you can have in this background. And there are 10 possible choices of G-flux terms in the background, which does not violate the de Sitter isometries. All possible derivatives, N1, N2, N3, and N0. N0 is the derivative with respect to time, and these N1 is the derivative with respect to this the base. M and alpha are the base of the non-Kähler manifold, and A is the 11 direction. And then you contract it by a metric, raise them to arbitrary power, L1, L2, L3, L2. So there are 38 possible choices here. This is one possibility, of course. And then sum over all Ni, Ni. This will be the exhaustively all possible perturbative term you can think over. Not only that, N1, N2, N3, and N0, they can also be negative. You can have inverse the derivatives. That's also possible. So you not only take all possible derivatives, we also take all inverse derivatives. On the other hand, L1, L2, L3 could be integer. Of course, we don't know what is inverse of the curvature tensor. So we'll take them positive, but derivatives can become negative, of course. And this is the distribution. M and N are the coordinate of M4. Alpha, beta are coordinate of M2, and AB is the coordinate of torus. So this is the 8-dimensional space that we are talking about. So this would be a possible perturbative thing. And sum of all of these perturbative terms could combine to give a huge perturbative sector of them here. So question is, what is the perturbative energy momentum tensor? Well, you take the term and you take the derivative with respect to the metric, and then you'll get the possible energy momentum tensor from the perturbative part of the problem. You see, I've summed over also. Literally, there are an infinite possible term over here. Now, what is the metric ansatz? So this is my metric ansatz. I repeat it again. This is the space-time direction. This is the internal direction. This is the toroidal direction over here. What is the flux ansatz? So it appears there are three possibilities. One is that you take the fluxes in this particular way. So is the G flux. You see that G flux, it's a function of GS. GS is a time. So all the time parameter, I put it inside GS. So I split the flux as a space dependent thing and as a time dependent. So I split it up into space and time dependence in this particular form. M and PQ depends upon the base M4 cross M2. But there is also other possibility in which M and AB of the form where two legs are in the base and two legs in the toroidal direction. They are decomposed in this particular way. If you don't decompose in this particular way, you can show that if you dualize back to type 2b, you violate the de Sitter isometry, which we don't want. Then there is also a space-time part of the G flux, which is of this particular form. So this is my ansatz of the G flux. Note that if I take k equal to 0 in this particular equation, then I get a time independent flux. But there is more. For example, we want to know how this F1 and F2 coefficient of the metric behave. Again, F1 is purely a function of time, F2 is purely a function of time. So I raise them to arbitrary power of time over here and sum them up, all possibilities. But we also want to keep the Newton constant same, which means that F1 times F2 square has to be equal to 1. This leads to the following constraint on CP and DPs. So the constraint is the following. From there, you can easily read up all the possible values of CPs and DPs. Now, having made the ansatz and having chosen the infinite collection of perturbative quantum terms, what strategy do we follow to determine whether the above background is consistent or not? Well, the answer is the following. In the given equation, Rmn minus half Gmn equal to energy momentum tensor from classical, energy momentum tensor from perturbative, and so on. We can simply compare the G-string scaling on both sides of the equation. You see the left-hand side has an Einstein tensor and the metric, which have G-string expansion because F1 of t have G-string expansion as we saw above. The energy momentum tensor of the classical piece has a G-string expansion because the G fluxes have G-string expansion. Remember, G-string is now a function of time, so you have to be careful. Question is, how about quantum term? Do they have nice G-string expansion or not? It took us 1 year to figure this out, and we found that there is a miraculous thing that happens. It turns out that the energy momentum tensor, no matter how non-trivial or arbitrary it is, it appears to have a G-string as G-string to the power of theta KL, where theta KL has the following unique form. This is the form of the power of G-string that appears from all the quantum term for one particular choice of quantum term for a choice of Li. Li, remember, are the powers of all the curvature terms. N1, N2, N3 are the derivatives along the space-time and the internal direction. 28, 29, 31, these are the powers of the G fluxes here. K is the coefficient of the power of the G flux that appears in the ansatz. Now, L1 to L27 are the powers of the 27 possible curvature tensor coefficient that you can have. And somewhat miraculously, all of them have exactly the same power of 2/3. This background is the choice of the ansatz of de Sitter has something miraculous built inside them, because you can take any curvature tensor and you can easily see that if you plug in the metric answer, the time factor just simply purely isolates out, and the power of the time factor or the G-string power is exactly 2/3. Okay. L28 to L38 are the power of the G flux coefficients over here. And these 36, 37, 38 are these localized G flux that we talked about before, of the form 2 legs in the internal space and 2 legs on the toroidal direction. N3 is the number of derivatives along the 11 direction. Note something interesting. Note the relative minus sign. There's a minus sign over here and there's a relative minus sign. Everything else is plus. There are 2 places where there's a relative minus sign over here. They occur in 2 places, as I said, in front of N3 and in front of L36, 37, 38, which are basically the localized flux of the form G, M, and A. Okay. So I can pause a little bit to ask if there's any question so far. If not, so let's see what goes wrong if we take time-independent fluxes. Now, what is time-independent flux? Time-independent fluxes means you take k equal to 0. This gives us the following thing. I put k equal to 0. You see that the power of the perturbative term become G-string to the power of theta KL, where theta KL takes this particular form. So you see, I can collect all the positive part and call it stuff, and collect all the negative part, call it stuff prime. So it becomes stuff minus stuff prime. Okay, we don't have to worry about what are these, but you can see the negative one coefficients are the one exactly with 36, 37, 38 means GM and AB to the power of 36, 37, and 38. And a number of derivatives along the 11th direction. This is not a good sign, as you will see. Why is that? Now recall what was our strategy by which we want to solve this equation. The way we wanted to solve our equation is to balance the G-string power on both sides of the equation. Now what this entails are the following. So this was my equation, R mu nu, Rmn minus half Gmn equal to the energy momentum tensor. Now Rmn is a function of Gs, which means this Gs contains all the time. So Rmn is a function of time and the coordinate of the internal space. Gmn is a function of time and the coordinate of internal space. The Ricci scalar is a function of time and the coordinate of internal space. And the energy momentum tensor are a function of the coordinate of internal space and the time. So time is already put inside. Which means that, look at the GMN piece, you can extract out the G-string dependent of the GMN piece and write it as the time part you can isolate over here and write it as a time dependent part and a space dependent part. Now you see the classical piece TMN classical, you can write it as a time-dependent part and a space-dependent part. But the quantum part, which is the infinite collection of perturbative thing, nicely separates into G string to the power of stuff minus stuff prime and the perturbative energy momentum tensor. And the dotted terms are all the non-perturbative, non-local topological pieces, which I'll not discuss for this particular talk. Now you can easily see what is the problem here. We have lost the G string hierarchy completely. Why is that? Imagine I choose a particular, let's look at this equation. Imagine I want to solve this equation. So I have to choose a theta E equal to theta F to the same order in G string. Imagine I want to look at the equation for G string to the power of 0, G string to the power of 1, G string to the power of 2, and so on and so forth. So I want theta E equal to theta F, for example. Now you see when theta E equal to theta F, you see there is literally an infinite number of stuff and stuff prime possible. For example, imagine theta E is 0 and theta F is 0. That means stuff minus stuff prime should be equal to 0. If I give you an equation A minus B equal to 0, there are literally an infinite possible solution for A and B. Imagine I choose theta E equal to 1, theta F equal to 1, then stuff minus stuff prime becomes 1. So there is so I have an equation of the form A minus B equal to 1, and literally there are an infinite number of possible solutions for A and B, which is equal to 1. But wait, you might say, okay, maybe we lost all the, so let's just go back. You see that for every choice of stuff and stuff prime, that means every choice of stuff, I get these powers of L. Stuff prime means I get a power of S, means every choice of these two factors, I get different operators. So all of these operators, there are infinite collection of operators now having the same G string power of the G string. But wait, you might say that, all right, the operators all have different G string, but they also have different they have the same G string, but they may have the same M-Planck power. So they may, so I apologize, I said the wrong thing. All the operators have the same G string, but they actually have different M-Planck scaling. Means every operator, say curvature to the power of 32 and curvature to the power of 15, they in this case probably will turn out to have the same G string, but they will have definitely different power of M-Planck. So couldn't we take M-Planck to infinity and get rid of this apparent loss of G string hierarchy? Is it possible we can take M-Planck to infinity and get rid of this hierarchy? It turns out that it's not. The answer is no. Now this is because the troublesome operators that seem to break the G string hierarchy are constructed out of the localized G flux. As I told you, they are constructed out of L36, 37, and 38. So they are related to these localized fluxes. Now, if you stare at the localized flux for some time and you ask what kind of localized flux are there, it turns out this localized flux are Gaussian, localized function given in terms of Gaussian. So these localized fluxes have secretly M-Planck scaling inside their definition. But that's not good, because remember, we also have derivatives along the 11 direction, which is the appearance of N3. So if I imagine I give you e to the power of minus mp square x11 square. If I take a derivative with respect to x11, then you can easily see that the M-Planck factor comes in front. This M-Planck factor will tend to kill the M-Planck suppressions in the quantum term. As a result, to any given power of G string by A and M-Planck to the power of B, there are literally an infinite number of operators, thus killing both the G string and the M-Planck hierarchies in the system. Loss of G string and M-Planck hierarchy means that there is no simple description, effective field theory description in 4 dimensions with de Sitter isometries. Now, I just gave you an example with perturbative quantum terms. Even more drastic violation of effective field theory happens with non-perturbative topological and worse with non-local counter terms. Thus, we cannot get de Sitter with any classical sources that we already saw and that I already discussed in our 1402 paper. And now we see that any amount of quantum terms cannot give rise to de Sitter solution as long as the flux components are time independent. So if you have a de Sitter vacuum and you have fluxes to support this de Sitter vacuum, you have fluxes. If the fluxes are time independent, this system is in the swampland. There is no possibility by which we can ever have a de Sitter solution in string theory with time independent flux components. Nothing can save the day, and these backgrounds are truly in the swampland. Note that we have derived our result by going deep in the core of M theory and type theory without using any ad hoc hypothesis. So Vafa is not wrong when he said that these backgrounds are in the swampland. These background, there is no way you can save this background. There is no de Sitter solution with time independent fluxes. And no matter how many quantum term you use, perturbative, we check every perturbative possibility, every non-perturbative possibility, every non. We even check e to the power of thing, and we even check e to the power of e functions like that. We tried to do Borel sum of them. We did the trans series. There's no way you can save the situation. There is no de Sitter solution with time independent flux component. It's definitely in the swampland. But that's not the end of the story. Clearly, if we take k greater than 1 in our expansion, that means if we take time-dependent G-flux component, we miraculously regain both the G-string and M-Planck hierarchy. Thus, it appears that 4-dimensional space-time with de Sitter isometries and time-independent Newton constant does exist in the string landscape if we take time-dependent G-flux components in the account. These are all weakly coupled background. No matter, even if the coupling is varying with respect to time, these are completely weakly coupled background. Their energy scale are always small, much, much smaller than M-Planck. In fact, it turns out that we can do even better. We can realize the above background as a Glauber-Sudarshan state over supersymmetric Minkowski background. It turns out that the supersymmetry is broken by coherent state, spontaneously. And because of the supersymmetric Minkowski background, the 0-point energies cancel. And here comes something nice. That means the cosmological constant appear exclusively from the fluxes and the quantum terms with no contribution from the 0-point energies. Here comes another nice thing. Wilsonian analysis can be performed because the modes of the theory are secretly the modes over the Minkowski background with time independent frequency. So the modes that we see, which are time dependent frequency for the de Sitter, are secretly can be thought of as a secret combination of the time independent modes. So Wilsonian analysis can be performed in this background. This means that TCC is no longer an issue for us. Transplanckian cosmic censorship is not an issue for us. This all appears to be encouraging, but we cannot declare victory and go home yet. And that is the next part of my talk. But before I go into it, I would pause and ask if there is any question.
Yeah, I have one question.
Yes, yes.
When you say that the G flux is time dependent,
yes,
you're not implying that the quantized G flux is time dependent, right?
Good. I'll talk about it. Quantization of the fluxes. I'll come to that. Okay. Anomaly cancellation, quantization, a lot of other issues. That's why I said this appears to be encouraging, but we cannot declare victory and go home yet.
I see. Okay. Thank you.
Because there's lots and lots of issues now we have to resolve. So this is not a simple matter. But thanks, Ashok, for asking this question. So question is, why is finding, now that we have said something, it's appear like de Sitter is possible. So why is this a hard problem? Something already Ashok pointed out in some sense. Okay, the first and the foremost question is to solve the time-dependent equation of motion, which are the supergravity equation of motion in the presence of all possible quantum corrections. Now, this by itself is challenging, but it appears after 1 or 1.5 years of work that with time-dependent degrees of freedom, we can do it. But equation of motion, however, can only provide a local picture, but the existence of a solution is not a local thing. It's, or even the existence of a Glauber-Sudarshan state relies heavily on global constraint. That's more important than local constraint. Just by solving equation of motion is not enough. We have to make sure of the global constraint. And just now a question was asked, the global constraint come from flux quantization, anomaly cancellation, moduli stabilization, etc. So we not only have to solve the time-dependent equation of motion, but also show the following explicitly. Show how the system is quantum mechanically stable. Are there tachyonic direction in the system? So far, our analysis has shown that it's possible that the system may not have a tachyonic direction, but that needs to be explicitly checked. Now, here comes the question. Explains how flux remain quantized with time dependencies. You cannot put, see here, the big problem is that you cannot just throw in time-dependent fluxes in a compact space. These fluxes has to be quantized. Now, Witten has said that the fluxes are quantized by g to the power of 2 pi and then the Pontryagin class. But these are all for time-independent theory. Now we are in a completely new situation in which we have complete time dependence. So how on earth can we say that the fluxes that we put on a compact space is quantized? It turns out that you can show that the system is quantized if you carefully look at the variation of the fluxes as well as the variation of the manifold. So I discussed this in my paper, how the quantization of fluxes can happen. But quantization of flux is not enough. You have to show how anomaly cancellation works, because how Gauss law, you cannot throw in fluxes in an internal space because the system is completely inconsistent. You have to show how anomaly cancellation works. Now this turned out to be a highly complicated problem, but we can show that the choice of fluxes, the way we arrange the fluxes to vary with respect to time, if you carefully take all the quantum correction into account, you can show that the anomaly cancellation does work. The reason is that if you may remember, the anomaly cancellation of the G flux is equal to integral of G where G plus number of M2 brane is equal to the integration of, is equal to the Euler characteristic of the manifold. But now everything is time dependent. Integral of G where G is time dependent. The M2 branes are moving, they are time dependent. It turns out that the Euler characteristic comes out of integral of this X8 polynomial. Now the X8 polynomial itself becomes time dependent. So you see that the anomaly cancellation becomes a time dependent equation, and one can show that it's rather a very interesting calculation in which you can show that the G string dependence simply go out in a very beautiful way, and at every instant of time you can show that the system is anomaly free. Similarly, at every instant of time you can show that the fluxes remain quantized. Now, next comes another bizarre question: how moduli stabilization understood when the moduli are themselves varying with respect to time? See, here again we encounter a completely new situation in which the system. Yes.
I have a very elementary question. How can you have quantized flux which is time dependent?
No, what I mean is that so it's integral of G is equal to, so G becomes time dependent, okay? And then I have, so integral of G is equal to Z, but it turns out that integral of G has a time dependent piece, and the Z come from the moving M5 brane and the quantum term that has a time dependent piece. So if you remove the time dependent piece, at every instant of time, you can show that integral of G is equal to Z.
But if you choose your variables to work with quantized flux from the beginning,
yes,
this should be automatic, right? I mean, instead of allowing the G fluxes themselves to be arbitrary variables, suppose you take the integers fixed, because integers are not going to change continuously with time,
correct,
right?
correct. Yes, the one which depends upon the Y are automatically that's exactly what I mean, that the one which depends upon Y, they are automatically quantized. And it appears to us that the G string just comes in for a ride in this equation and it just decouples completely.
Okay.
We check these things.
Because the compact spaces are expanding or contracting, right?
Yes, that's right.
Okay.
Yes. It's a bizarre situation, but after a lot of work and talking with Witten and all, and eventually figured out there is a way out of this mess.
And so one shouldn't really think of the fluxes as independent variables, right? Because
yes,
they will be determined by the size of the compact dimensions.
Correct. So we have to solve the flux equation of motion and show all of these things to be consistent. I just showed you the Einstein equation of motion, but you also have to solve the flux equation of motion to so that it all can be consistently realized. Okay. It's a big system with a lot of moving parts. Okay, but that's not enough. How are the no-go conditions are satisfied? We have to show how the no-go conditions are satisfied. How are the null, weak, and strong energy conditions are overcome? That's very important. Otherwise, we cannot say that there exists a solution. Now, how the generic perturbative correction may be analyzed? We just showed that it's a polynomial powers. The reason why we showed them as a polynomial power is because we are at a weak coupling and we are assuming that the time independent piece of the fluxes can not be very large. But in generic perturbative correction, how can they be analyzed? How the non-perturbative correction may be analyzed. But one good thing about here is that typically some of the non-perturbative goes as e to the power of -1 over G string. And then the limit at late time, which is what we look for in cosmology, G string goes to 0. So e to the power of -1 over G string goes to 0. So we thought that maybe the non-perturbative term completely decoupled, but this was not the case actually. There are other non-perturbative terms which actually survive in this thing. So we did have to take care of all of these things. How are the non-local quantum terms may be understood? Because as we know, M theory also have non-local counter term. They are not visible at low energy, but there are non-local counter term. And for example, in our perturbative analysis, we took the inverse of the derivative. If I have a 1 over box to the power of 300 is a highly non-trivial, non-local term. And they contribute, actually, they do contribute, not exactly at low energy, but they do contribute in some indirect way. So they need to be understood because since we don't know what M theory exactly is, what is inside M theory, we don't know. So we can have to play whatever possibilities are there. Of course, many of these terms may be summed as a trans series by you can borrow some of all of these, then we'll get exponential of these terms. We have to deal with, since we don't know exactly, we have to deal also with exponential term. Sometimes we get e to the power of exponential to the power of exponential to the power of quantum term. Those terms could also be there. Again, ignorance is an issue here since we don't know what is there inside M theory. So whatever comes to mind has to be taken into account. How the 4-dimensional Newton constant may be kept constant. We check that F1, this Newton constant in our analysis remains time independent. Question is, do they get renormalized? So that's another question. Our analysis show that there is a small renormalization of the Newton constant. There is a finite renormalization of the Newton constant, but it remains time independent throughout that interval in which the system is weakly coupled. But they do get renormalized. Now, how the positive cosmological constant may be generated by quantum correction. We not only have to show that the positive cosmological constant may be generated by quantum correction, we also have to show that the cosmological constant itself is time independent. That was a little bit hard to show, but we eventually managed to show that the cosmological constant can remain completely time independent. And indeed, it can be shown that it's positive definite in this case. So it is a de Sitter background. It's not a quintessence, definitely not a quintessence. It is a de Sitter background, definitely de Sitter background with positive cosmological constant, a renormalized Newton constant, but Newton constant is again time independent. How does the 0-point energy get renormalized in a non-supersymmetric background? These backgrounds are highly non-supersymmetric. How does the 0-point energy get renormalized? This was a big problem which we did not know how to solve in the beginning. Finally, we figured out that if we view it as a coherent state or a Glauber-Sudarshan state over a supersymmetric Minkowski background, then because of the background being actually supersymmetric, the 0-point energy cancels thanks to supersymmetry. And the de Sitter space actually becomes coherent state or a Glauber-Sudarshan state, as we call it, because coherent state, I know it's in quantum mechanics, Glauber-Sudarshan state, or sometimes people call it Glauber state. It's in the quantum field theory language. Now, supersymmetry there in the Glauber-Sudarshan state is broken spontaneously. So it's the spontaneous breakdown of supersymmetry happens because the fluxes themselves are not self-dual. So you can arrange the fluxes which break the supersymmetry spontaneously. Next come how the geometry and the topology of the internal compact space, which is now a highly non-Kähler manifold, may be expressed. Since you can explicitly show that Calabi-Yaos are not solution for this system. So the internal space is a highly non-Canard manifold. How can they be expressed? Next, how the Bianchi identities are satisfied in a time-varying background. These are related to the flux quantization. Also, the Bianchi identities. And it turns out that the Bianchi identities, if you write down the Bianchi identities, the perturbative correction contribute to the Bianchi identities, and the Bianchi identities get augmented by these quantum pieces. And you can show that so this is one thing we found to be interesting, that de Sitter is a very special background in which somewhat miraculously the G string or the time dependence somehow rather beautifully decouples. That's what we found of de Sitter. So there is some reason why nature is de Sitter, I think. There may be some deeper reason beyond that. How the Swampland criteria are reverted. I mean, when Bafa put up his original paper, he said delta V by V should be greater than C. Actually, if we now have a solution, you actually can compute delta V by V because you can calculate the potential from all the perturbative and all. And you can explicitly show that delta V by V is exactly greater than 1 over G string. Since G string is 0, very close to 0 at late time, it's much, much bigger than 1. Now, we talked about late time physics. Question is, how is the early time physics should be understood? How the inflationary paradigm may be recovered from our analysis. We simply cannot, unless we recover the inflationary paradigm, we cannot again say that the system is solved. Now, how other solutions like Kastner de Sitter or dipole deformed de Sitter could be studied. And there are many more. I don't have time to discuss more. All in a top-down string theory setup. But you can see that most have to be solved. Otherwise, cannot claim that we have a de Sitter solution. We cannot say that I will solve the Bianchi identity tomorrow and this is my solution today. You cannot come up with a solution in which Bianchi identities are not solved, or anomaly are not cancelled, or the fluxes are not quantized, or the moduli are not stabilized, or the internal Kähler manifold is not consistent, or the fluxes equation of motion is not solved. If we have to solve each and every problem, then only we can declare that de Sitter is a solution in string theory. So that makes the problem a very hard problem, because not because that we might have a solution. The question is that the solution comes with an extra baggage. All needs to be solved simultaneously. Otherwise, for example, we cannot say, unless we check that the cosmological constant remains time independent under all quantum correction and under all possibilities at every instant of time, it's not a solution. We also have to check that the Newton constant does not get time dependent, some kind of renormalization, or it has to be some time independent renormalization. It can get renormalized, but at every instant of time, it has to remain time independent. Otherwise, it will be a quintessence background. You see, everything has to be solved together. And this is, in my belief, makes it a very, very hard problem in physics. It's not the situation that we can just say that we solve some part of it and go home. Moduli has to be stabilized. You have to give a meaning to stabilization of moduli and so on and so forth.
Keshav, I have a small question.
Yes.
Yeah, actually, you could have taken de Sitter to be an static patch. No, why you are taking that to be a time dependent? So everywhere you have a time. You could have worked with the static coordinates.
I could have taken the static coordinate, but the horizon become observer dependent. So that means observer are moving with respect to that patch, right? So that was much harder for us to do, because we could not figure out how to put this in string theory in which the observer is moving with respect to time, and then how to determine the fluxes. So we took a patch which is the, 1 over lambda t square kind of thing, in which we knew that the observer doesn't have to be moving, and we can put the time dependent fluxes like that. I could have done it like that, in which case all these things which I'm saying are hidden in a different way.
Okay.
Yes, we thought about this. Thank you for asking this question. We did think about that one. So now it turns out that although it's a hard problem, it appears to be a doable problem. Actually, we need a lot of effort, goes in, but it's still doable. We showed how explicit time dependencies of the fluxes may allow de Sitter solution to exist in the string landscape. Now, due to many reasons, the solution is most succinctly expressed as a Glauber-Sudarshan state over supersymmetric Minkowski background. Now, I have to apologize to Diwali because we originally did not cite his paper because we did not know that he actually already in 2017 he came up with this conjecture that de Sitter has to be a coherent state. But he was dealing with 4 dimension. After we wrote the paper, he pointed us that he had also thought about this one. Lucky for us, he didn't scoop us because he was doing typical in quantum gravity. We were doing in full string theory. So I should point out that he was the first person to point out that de Sitter has to be a coherent state. We could make everything explicit, and we showed how this could be done in string theory. But you should definitely look at this paper by Diwali in 2017. He has been writing a series of papers on that subject, very beautiful papers. Unfortunately, we were not aware of them, but now we know that even it turns out that we are also trying to show that even the inflationary evolution of the universe could also be thought of a evolving de Sitter space, evolving coherent state.
Keshav, how much more time do you need?
I'm done. It's just two more seconds.
Okay.
It turns out that the equation of motion are, it turns out in this language are the Schwinger-Dyson equation. The coherent state is generated by displacing an interacting vacuum, which you may look into our thing. I told you moduli are stabilized. So no Dine-Seiberg runaway is there at every instant of time. We call this is new and we call it dynamical moduli stabilization. There appears to be no problem with TCC and Wilsonian effective action can be written down, which was good for us. So to conclude, as of today, it appears that we are still living in a de Sitter space, or more appropriately in a de Sitter Glauber-Sudarshan state. Finally, last but not the least, how I stopped worrying and started liking the time-dependent backgrounds. I was always scared of those backgrounds. So I thank you for your attention.
Thanks, Keshav, very much for a very nice talk, very comprehensive. Maybe we have time for 1 or 2 quick questions.
Can I ask
Keshav,
one question?
Just a small question. Can I ask?
Yes, please.
In the end, you mentioned that the cosmological constant should also be time independent. Is that really necessary? It can also be in the real world, it may be having a very small time dependence.
Yeah, I had a long message from Andre Linde a few days ago.
Oh,
Gave me 10 different arguments to convince me that is the case.
I see.
On the other hand, Robert convinced me that this is not the case. So I don't know which side to bend.
Okay, all right. Okay.
One of them gave me a postdoc position. Other gave me a job. So I don't know.
Okay. Thank you. Very nice talk.
Thank you very much.
Okay, if there are no more questions,
I have a very quick question, actually.
Yes, please.
So in time-dependent case, you typically have this infrared issues, right? Which gives some infrared time dependence in coupling constants too. For
Absolutely.
example, so is it something special about this state that you're avoiding this infrared issues?
There are infrared issues, and I wrote a paper on that a few years ago on this, discussing that. It turns out that to make it short, this infrared issue in this in the time domain is not very bad, but it turns out that if you view it as a Glauber-Sudarshan state, okay, where does the time infrared issue comes in? The infrared issue comes in because we can go to very short distances. Okay, we can go to very large distances. Sorry, not short distances, very large distances. But here, everything is constrained under the Hubble patch. So this is one way of saying that there may not be this IR issue. The other thing is that when you view them as a global Sudarshan state, then these issues do not tend to appear because of the fact that the frequencies and all are not time dependent. And I can tell you in more details about all this thing. We did discuss this in our paper.
And then if you say that the cosmological constant is somehow dynamically generated, it's not fundamentally there. So, so isn't it too much to expect? It would be a time dependent, completely time dependent. I mean,
no, it is not.
It might be.
No. That was our biggest worry in the whole analysis, that since the 0-point energy has no contribution in this kind of thing and is generated from the fluxes and the quantum terms, we thought that since the quantum terms are time dependent, the fluxes are time dependent, the cosmological constant will become time dependent. It turns out that if you actually calculate the lambda, all the time dependencies cancels out. Very nicely they cancel out, and you get lambda which is completely time independent.
And it can be tuned to anything you like, or is it something fixed?
That part we are not 100% sure. We need to actually work out. Since we see, the problem is that we know it is dependent upon the quantum term, but we don't know what is the coefficient of all the perturbative quantum corrections. Okay, and remember I showed you this infinite collection of perturbative quantum corrections. They contribute to the cosmological constant. But how do we know that curvature to the power of 32 exists in M theory, or under effective action or under Wilsonian effective action such? And what is the coefficient of that? Does it come with a +5 plus something by M Planck, 5 by M Planck, or something by M Planck? We don't know the exact coefficient of these terms. So we do not, we know it's time independent, but we don't know what is the precise value of this one. We do know that it's small. There is a reason to suspect why. Yes.
No. Yes. I mean, is this somehow related to Starobinsky model? Or
I don't know much about the Starobinsky model. So
because there also he just took the Riemann square and you get a solution. Right? I mean, he wrote of course in the static patch, but you could do it in the coordinate system that you are using.
Yes.
And there also you have a time independent cosmological constant.
I need to look into that. I don't know much about that.
I see.
Okay.
Thank you.
Thanks very much for patiently answering all the questions, and nice talk. We will move to the next talk of the session, which is by Alok Laddha. And he's going to talk about polytopes and scattering amplitudes. Alok, if you're here, you can please share your screen. Please,
yeah, I'll just share. Can you see the?
Yes.
Yeah, you can see that. Okay. Yes. I have to do full screen.
At the top, there's view.
Okay.
There's a view button at the top.
In the
top, further up.
There's a more. I see.
No, on the left.
It's Acrobat Reader. Control L will do it.
Okay.
L.
Yeah, full screen. Yes, it's great.
And you can see the mouse also, right?
Yeah, we can see that.
Okay. Yeah, I can start whenever.
Yeah, please. We are great to have Alok Laddha from Chennai Math Institute. He's going to talk about convex polytopes and the S matrix. Please take over.
Okay, thanks, Shubha. So first, I would like to thank Tanay, Ayan, and Suresh for giving me a chance to speak here in a really nice conference and very, very smooth organization. It's quite impressive. And I'm going to talk about some recent progress in the amplitude-hedron program in understanding scattering amplitudes in non-supersymmetric quantum field theory. So don't worry if you don't know the words, and it more will be like a review talk where I will introduce at least the basic ideas involved. So mostly I will talk about the work that I have done in collaboration with Anish, Pinaki, Brunmay, Ranjan, and Sujay. Anish, Brunmay, and Sujay are students, and Pinaki and Ranjan are postdocs. And there is also some ongoing work with Brunmay, part of which we released recently, and there's some ongoing work. Okay, so let me just start with some motivation first. So of course, as everyone knows, scattering amplitudes or S matrices are fundamental objects in quantum field theory. But I mean, even though they are so central, they are kind of elusive in some sense. And we keep seeing new structures even in perturbative domain. For example, yesterday in Andrea Poom's talk, we saw how to write amplitudes as two-dimensional correlatives on the celestial sphere. And I think the status of S matrix is aptly summarized in a line in a movie called The Matrix, where one of the characters says that nobody can be told what an S matrix is. You just have to see it for yourself. So of course, we have kind of one definition of scattering amplitude in perturbation theory, which is via Feynman diagrams. So so you basically take so any n-to-m particle scattering amplitude can be computed by summing over all Feynman diagrams, up to a desired order in perturbation theory. But by now it's well known that Feynman diagrams obscure simplicity, and in many cases symmetries underlying the scattering amplitudes. Of course, the most famous example by now is the computation of so-called maximal helicity violating amplitudes in pure Yang-Mills in 4 dimensions. So if you try to do it Feynman diagrams, even a 9 gluon amplitude will have like 50,000 odd diagrams, but one knows that in this this amplitude has a very compact expression for any number of gluons, and so clearly something is amiss if you try to do it from Feynman diagram perspective. And there are other reasons also. I mean, amplitudes are on-shell quantities, and so by construction gauge invariant. But when we try to do perturbative computation based on Feynman methods or Lagrangian methods, they obviously force us to consider fields as fundamental quantities. And so we have to go off shell in order to do these computations, and they introduce kind of unnecessary complications. And that's part of the reason why some of these complications are easier in formalisms where we always stay on shell. Hopefully some of this will become clear in the talk. So even leaving aside the question of how to efficiently compute scattering amplitude, we can ask a more conceptual question in the sense of how much do Feynman techniques really tell us about what the definition of a S matrix is, even a perturbative S matrix. And to answer this question, we need to really look at what are the core postulates which any definition of S matrix has to satisfy. And of course, there is the core postulates maybe can be summarized in these four things: unitarity, Poincare invariance if we are in Minkowski space, crossing symmetry, and maybe some most subtle postulate which is known as maximal analyticity. And in many ways, this is one of the key postulates. And I mean, essentially, the postulate basically says that if you take the full complex plane spanned by all the Mandelstam invariants, then only singularities of an S matrix are those which are consistent with unitarity and causality, or if you are in Minkowski space, locality. I mean, they are the same things in Minkowski space time. But the singularities of a perturbative S matrix are hard to classify even in perturbation theory. In fact, the full structure of singularities is, even for scalar field theories, is very complicated. And there's this nice quote in Itzig and Zuber that study of complex singularities in scattering amplitude is very complex. So the question kind of we want to ask is, how do we classify functions in complex Mandelstam space which are Lorentz invariant, unitary, and represent analytic S matrix? So that's really the central question that we are interested in. So in a nutshell, I mean, we don't really know a definition of a perturbative S matrix structurally, but we have many representations, Feynman, BCJ representation, which makes the color kinematics duality manifest. There is the famous CHY representation, and as you saw yesterday, there are celestial amplitudes, for example. And one extreme examples of these different representation, of course, in ADS, where you have ADS CFT, where you have a ADS amplitude can be represented as CFT correlation function on the boundary. And in all these examples, we see that properties which are manifest in one representation are obscured in the other representation and kind of become corollaries in the other representation. So the question that I asked in the previous slide, maybe we can like sharpen it a bit and ask if there is a framework of scattering amplitudes in which all these different revelations can be unified in a given framework. And if there is, what are the fundamental postulates on which such a framework is based? And it is this, with this goal in mind, this is the basically maybe the central goal of the amplitude hidden program. It's a new perspective on amplitude which aims to encompass different representation of the perturbative S matrix. And hopefully I'll try to convince you that it does offer radically new insight on what at least on what a perturbative S matrix is. So let me before going into the more quantitative details, let me try to summarize the key ideas which are involved in the program. So the idea is that we start with a very bare bone structure. For example, say a space of Mandelstam invariants which is usually called the kinematic space. The subscript n denotes the number of particles that we are scattering. And now the idea is that we want to build S matrices from scratch for different theories. So the question we want to ask is, what are the minimal set of principles we can invoke and build S matrices from such a bare bone structure of just like basically having kinematic space? And this question was partially answered in a remarkable paper by Arkani Ahmad, by He and Yoon, who showed that for a massless phi cube theory, but where the scalars are colored, in any space-time dimension, there are some objects sitting in this kinematic space. I mean, they are just some polytopes, like convex objects, which are known as associahedron. And they are really sitting in the positive region of the kinematic space. So where all the Mandelstam invariants are positive. These objects are very interesting in the sense that all the boundaries of these polytopes correspond to all singularities of the tree-level scattering amplitude of phi cube theory. And based on this realization, they showed that associated to each of these polytopes, there is a unique differential form. And this form is indeed the scattering amplitude for the theory, for the phi cube theory where the scalars are colored. So just starting from kinematic space and just locating this polytope gave them an amplitude for a theory. So that was the kind of the start for this program in non-supersymmetric corner field theory. And this polytope, which is called associahedron, I mean, this is a known polytope in mathematics literature for many decades. And it has many fascinating properties, which I mean, I just list some of them which are most relevant for us for physics. So one is that it has, if you take an n-dimensional associahedron, it has boundaries of all codimensions. So it has boundaries all the way up to a vertex which is 0-dimensional, and these shapes are called positive geometry. So one counterexample to positive geometry is a circle, which is a 1-dimensional manifold, but it doesn't have any boundary of zero dimensions. And there's a general result in mathematics literature that if you take any positive geometry of say dimension n, then it has a canonical, unique n form, which has this property that this form has simple poles on all the boundaries and nowhere else. So it's definitely, it necessarily has simple poles on all the boundaries, and it necessarily does not have pole anywhere else. And such a form is unique. Another really striking property, which is not generic for polytopes, is that if you take any boundary of associahedron, it's always a product of lower dimensional associahedron, nothing else. So just to give you an example, if you take 1-dimensional associahedron, as we will see, it's just a line with 2 vertices. So it's just a simple polytope. So of course, its boundaries are 2 vertices, which are 0-dimensional polytope, 0-dimensional associahedron. If you take 2-dimensional associahedron, then it's a pentagon. So what the above property implies is that if you take a 3-dimensional associahedron, then all its boundaries can either be a pentagon or square. Square is a product of 2 lines. But for example, there can be no boundary which is a hexagon or octagon or something. And as Arkani Ahmad and his collaborators showed, that it is this property which is responsible for giving us an amplitude which is unitary and local. So the unitarity and locality of the amplitude just is a consequence of this, this particular property of the associahedron. And this analysis then was later extended by Arkani Ahmad, Hayes, Salvatori, and Thomas to one-loop integrands for the same colored phi cube interactions. And so with that small review, let me just tell you what we will try to do in this talk. We will show that actually the framework that ABHY introduced is very general. And in fact, for any phi to the p interaction, there is actually a natural class of polytopes which are known as accordiahedra and pseudo-accordiahedra, which determine tree level and integrands for one loop amplitude for any phi to the p scalar field theory. And as hopefully I'll try to convince you that these are actually very simple polytopes to construct. They really just require some linear algebra and combinatorics, and come from just looking at some dissections of a polygon. This point will become clear in the talk. And the pseudo, I mean, one interesting offshoot that we found here was that the pseudo-accordiahedras are polytopes we found because we were interested in one loop phi-4 scattering amplitude. So these are, I mean, new polytopes which haven't really been explored by even mathematicians here. And okay, so before I go into now the details, let me just make a disclaimer that we will work with color ordered amplitudes, or in other words, what are called planar amplitudes. So we implicitly assume that all scalars have color degrees of freedom in the adjoint, or what is usually used in this literature by adjoint representation. Although we will never display color indices explicitly because they are not important for us, what we want to discuss here. And the reason for this is simple. These ideas are perhaps best developed for these so-called planar amplitudes. But I just want to clarify that planar here does not mean large, and it just means that we are working with amplitudes which are color ordered. And although for just because of lack of time, we will work with massless particles. It's actually perfectly straightforward to generalize this result at least to a single massive scalar field. Again, if the scalar has a color degree of freedom. Okay, and now this is the so maybe I can stop here and see if there is any question on the motivation. Okay, then I will just go ahead.
Sorry, Alok, I have a quick question.
Yeah.
Is there any way to generalize this to higher loops? I mean, why does it stop abruptly at one loop or something? You know, is there some recursive relations like?
So I think that so for phi cube theory, it has been generalized to all loops. The integrants have been generalized to all loops, but it's not published yet. I mean, this is a work which hopefully with Nima and his collaborators it will come out soon. So there the structures are far more it seems far more robust, and you are able to get polytopes which give you higher loop amplitudes also. For other phi to the p theories, we just haven't done it. I mean, it just.
Okay, thanks.
Alok, could you clarify my naive doubt?
Yes.
This generally boundary of a boundary is 0. So when you say that there is boundary all the way to 0 dimensions, what do you mean? It's in terms of some
just mean that if
discrete
you take a
objects?
triangle, then if you take a if you take a triangle which is 2-dimensional, then it has boundary of 1 dimension and boundary of dimension 0 also. So
you're counting each individual sides as boundary in this.
Exactly.
Boundary components, you mean then?
All boundary components, exactly. So I mean the contrast is with a disk which has a boundary of 1 lower dimension, but it doesn't have boundary of 0 dimension. So disk is not a positive geometry, but a triangle is a convex triangle is a positive geometry.
I understand. So it's boundary component really, because the total boundary will be the sum of these things, which is actually 0.
Certainly, yes, correct.
Thanks.
So just to answer your question more, I mean this entire there is a lot more development in this program in n equal to 4 super Yang-Mills theory, as you know, where the amplituhedron is a polytope for all loop amplitudes, not just So in that direction, at least in supersymmetric world, there is a lot more that one can set higher loops than in this.
Thanks, Alok.
Can you guys hear me?
Yes, we can.
Okay, now it says I've been muted by the host or something. Okay, so this is the rough outline of my talk. First show that when we start with this very bare-bone kinematic space, then there are these unique scattering forms that we can introduce, which really are determined by one single postulate called projectivity that I will try to discuss. So that will be like a fundamental postulate which will replace the other postulate like maximal analyticity, especially in the old S matrix program. And then I will review the work of Nima and others, that there is this convex polytope just sitting in the positive region of kinematic space. And once you know the form, the scattering form, and once you have this polytope, you can just compute the amplitude for tree-level scalar field theories. And then try to argue, if I have time, I will try to say how the whole thing extends also to in one loop for any phi to the p theory. Okay, so let me before I tell you exactly how the things go, let me introduce the basic structure, which is the bare-bone structure we are going to work with always. So the idea is to start with kinematic space, which is spanned by Mandelstam invariants. But we are interested in these color-ordered amplitudes, or what are called planar amplitudes. So the only Mandelstam invariants we are interested in are of this type. So you look at, for any I and j where I is less than j, you look at xij, which is this particular Mandelstam invariant, you sum from pi to pj minus 1. And one can actually show that the kinematic space is spanned by xij. So they form a basis for the kinematic space. They're a complete set. Now these xij's are also interesting because they have a nice geometric meaning. So if you consider any polygon, like abstract polygon, not living somewhere, formed by n vertices, and if you label the vertices clockwise, then you can think of xij as like internal chords of this polygon from I to j. Now, okay, so this is the raw structure we are starting with. We don't have anything else, but we immediately notice once we understand excises as these chords that there is a natural combinatorial object already sitting, in front of us, which can be defined as follows. So you take any set of excises which dissect the polygon into cells, like say triangles, quadrilaterals, or any other n-gon. And it turns out that the simple, as I will explain, simple combinatorics of these dissections can be used to construct abstract polytopes, combinatorial polytopes, and then this will become key for us to finally construct the amplitude. So let me give you two examples of these abstract polytopes, which are built simply out of this Xij geometric realization of Xij's as internal chords. So if you take, for example, triangulations of a pentagon, then if you consider all triangulations of a pentagon, then you get a convex combinatorial polytope, which is itself a pentagon. So if you notice that each vertex of this, so this is a combinatorial object that I was talking about. But if you notice, each vertex of this pentagon is a triangulation of the pentagon. So different vertices are labeled by different triangulations of a pentagon, and you can go from one triangulation to the other triangulation by only switching one of the internal chords. So you keep this internal chord fixed, and you switch this one to this one, flip this one. So going between any two adjacent vertices, you flip only one of the internal chords, and this way you generate this combinatorial polytope. This polytope is called associahedron. But at this point, it's a purely combinatorial object. It's not sitting in kinematic space or anything like that. It has nothing to do with physics so far. Now here it's an interesting, one thing I would like you to notice is that you could have started from any triangulation, like you start with this triangulation or this one, you'll always get the same object, because you basically span over all possible triangulations when you start doing this flipping from one triangulation to the other. But if you look at polytopes built out of say quadrangulations, I give you one example. So I want to do the same thing, but instead of looking at triangulation, I'm now looking at quadrangulation. Then it turns out that if you start with say this as a reference quadrangulation, and again you start looking at a polytope built in such a way that each vertex of this polytope is a quadrangulation of the, for example, in this case, a 8-gon. Then it turns out that this, you again get a pentagon, but this pentagon is sensitive to what you started with. So if you start with 1, 4, 1, 6, you get a pentagon. And you can show that if you start with 1, 4, 5, 8, then you will not get this pentagon, but you get a square. So if you start with any dissection except triangulation, then the combinatorial polytope you get retains the memory of the dissection you started with. But for triangulation, you always get the same object, a unique object, which is the associahedron. And that's why people, mathematicians distinguish between associahedron and all the other polytopes we obtain, which are called accordiahedra. So if you take a dissection Q of an n-gon, which is not a triangulation, then they are called accordiahedra. But if it is a triangulation, then it's an associahedron, because it's one object, always just unique. So okay, so now we have this just from the geometric interpretation of excises, we got these combinatorial objects. Okay, so this I just summarized the properties. So for any dissection Q, we get one combinatorial polytope, and if Q is a triangulation, then we have a unique polytope, and it's independent of the choice of Q that you start with. And this is associahedron. And if Q is anything other than triangulation, then you retain the memory of Q. So for different Qs, you get different polytopes. And there's a nice happy fact about these combinatorial polytopes, that dimension of the polytope, which is built out of say a pigulation, so a triangulation or quadrangulation, is same as the number of propagators in n particle amplitude with 5 to the p interactions. So of course, this is not a big deep thing. This one can easily see, but okay, it's a nice property to keep in mind. So for example, associahedron, which you build out of an n-gon, like triangulations of an n-gon, have dimension n-3, which is precisely the number of propagators you have in a Feynman diagram of n particles, with only cubic interaction. And so that's why associahedron will play an important role in the 5 cube amplitudes. Now we do the following. So now we have this combinatorial. Okay, maybe I can ask if there's any question on these combinatorial polytopes, because they are kind of central to us, what we want to do.
Yeah, look, this is Aninda here. I just wanted to ask a very nice question. What does boost, or what do boosts do to these polytopes? So
Aninda, right now they are just combinatorial. So we haven't really, they are just combinatorial. We haven't really attached them to any physical object. I don't know if that So we just take, we have n particles, and we just put the n particles in clockwise, and we have a polygon, and we look at different dissections of this polygon, and we build this polytope. That's it. It's a purely combinatorial object.
Okay, thank you.
Yeah. But also, maybe this is related to what you're asking. I mean, remember, we are always working with this kinematic space, which is Lorentz invariant. I mean, we modded. That's why we are only working with a Mandelstam invariant. So we don't really we quotiented out the action of the Poincare group. You know, from the we start with external momenta, and then we build a kinematic space where we have quotiented the action of the Poincare group.
Right. No. Yeah. Thank you very much.
Now we can start with this this abstract polytopes, and we can build an object which looks very counterintuitive from standard QFT perspective, but as you will see, it's kind of in some sense more natural than the amplitude itself, and it's a differential form that we can write down in the kinematic space. And this form. So let me first tell you what this form is, and then tell you what motivates this form, construction of this form. So the form we build in the following way: that you take each vertex of this polytope ACQ, like a purely combinatorial polytope, and you construct the following form. So you take any vertex. So each vertex is labeled by some chords, right? So for example, just to give an example, in this case, this vertex is labeled by 2 of the xij's, like x13 and x14. So with each vertex, you can associate a wedge product of whatever chords are occurring, like d log x13 wedge d log x14. And you sum over all possible such forms where the relative sign is such that start with any vertex and the adjacent vertex should have an opposite sign. I mean, that's it. So you sum over all vertices. Each vertex has an n-3 form now that you have associated, because each vertex has n-3 diagonals associated to it. And then you can construct this form. If you have a triangulation, if you have any other dissection, then you will have the corresponding number of a corresponding rank of the form will vary. I mean, in that case. So okay, but so this is the form that you could construct, and you can ask what is so special about this form. Now, for any Q, and this is the important point, that one can show that this form is projective, in the sense that if you scale all the xij's with the same function of the Mandelstam invariant, then this form remains invariant for any Q. And the reason this postulate was interesting is because it's the simplest kind of analog of dual conformal invariance in n equal to super Yang-Mills. Sorry, this should be 4 super Yang-Mills amplitude, where this principle is known, that the super Yang-Mills planar super Yang-Mills have dual conformal invariance, and the representation which made the computation of the amplitude most direct was the representation where this dual conformal invariance was manifest. So with that in mind, okay, we can ask, if we take massless theories which are not supersymmetric, do we have a postulate like this, and what can we do with it? So okay, if we take this as a fundamental postulate, then we get these forms, and these forms one can show are unique. I mean, once we have this postulate, then these are the only projective forms we can construct in the planar kinematic space, which have simple poles. So this is this is one thing that I should maybe elaborate on, that we are constructing forms which have a very specific pole structure, and the reason is that we want to somehow compute tree-level amplitudes to begin with. I mean, of course, eventually we will go to loops. So the idea that we want tree-level amplitudes, and that since we know that tree-level amplitudes have only simple poles, okay, so we want to look at forms which have simple poles, which these have, like dxij by xij, and they are projective. And then with these two principles, these are the unique forms you can associate with any accordiahedron ACQ. And the dimension of this form, the rank of this form is same as the dimension of the polytope. So for associahedron, this form will have a rank n-3. So that's what I say here. If Q is a triangulation, then this is a n-3 rank scattering form. It's unique, and it's in fact independent of what Q you started with, simply because the associahedron has no memory of the triangulation. So in that case, one gets just literally a unique form of rank n-3, not depending on any memory of triangulation or anything like that. It's just an n-3 form which is projective and which has simple poles. Let me give another example which is not a triangulation, which is more subtle. So let's consider quadrangulation of a hexagon. So now we are looking at these accordiahedra which are obtained by dividing a hexagon into 2 quadrilaterals. Now you can choose, there are 3, you can easily convince yourself that there are 3 possible quadrangulations: 1, 4, 2, 5, and 3, 6 of a hexagon. And then this form takes the following. So there are 3 for each accordiahedron. There is one form. So for 3 accordiahedra, there are 3 forms, and they have this structure. So they have a relative minus sign, and they have some poles on some channels in the Mandelstam variables. So we have 3 distinct forms. All of them are projective. So that's what fixed these forms. Okay, of course, so far these forms don't seem to have anything to do with amplitude. Because there are these relative minus signs. First of all, they are forms, they are not functions, and they are relative minus signs in amplitude, which we don't see in non-supersymmetric quantum. So, okay, so that motivates a question that, okay, we have this abstract polytope, associahedron or accordiahedron, and what can we do with it now to obtain amplitude once we have this form. So now we have a combinatorial polytope in our hand and these forms, projective forms, and now we want to build amplitudes from there. And now this is a gift of mathematicians to us, that these combinatorial polytopes, all of them are actually naturally sitting in the positive region of kinematic space. By positive region, I just mean that all the Mandelstam invariants are either positive or 0. And somehow all we have to do is like locate them, and locating them, finding them in the positive region was initiated by purely in with the physics ideas by Arkani Ahmad, by Hay and Yoon, but then it was formalized by mathematicians, especially Padrol, Palou, Pilot, and Plamandan. So the idea is that now this algorithm that mathematicians have given us, that you give me any combinatorial polytope and I can just find it in the positive region of kinematic space. And okay, I mean, this is just, I just wanted to mention, although I don't have time to get into this, that the way you locate them mathematically is because these combinatorial objects are realizations of some algebras. I mean, they're called cluster algebra and string algebra or gentle algebras. And it is this connection, this study of this algebra, which helps us finding these polytopes in the kinematic space. And there's a natural corollary to this, which is central for us, that it turns out that when you find them, the boundaries of these polytopes naturally coincide with the singularity locations of the tree level amplitude. So it's a very, so wherever the boundary of the associahedron lie will necessarily be a place where you have a pole in the phi cube amplitude, for example. But even though I can't explain how the mathematicians derive it because of lack of time, let me at least tell you what the equations are with which you can locate them in the kinematic space. And to do that, I just have to introduce one more relationship where which is between the Mandelstam invariant themselves, which is just the pi plus pj square, and these planar variables are introduced xij. And this is a simple linear relation like this that you can easily check. Now, once you have the Mandelstam invariants, this is the algorithm mathematicians give. So let me explain it first for triangulation, and this way we will be able to locate the associahedron in the kinematic space. But the algorithm is much more general, and we can do it for any accordiahedron. So if it is a triangulation, take any triangulation, it doesn't matter. Just start with one triangulation and look at a triangulation that you obtain by rotating t counterclockwise. So you get, if t was say 1, 3, 1, 4, then the counterclockwise one will be phi 2, phi 3, for example. And then you just put these constraints. You say Sij are minus Cij, where Cij are positive. So you freeze all the Mandelstams if Ij's are not in Tc. For all the Ij's not in Tc, you freeze this Mandelstam variable. So intuitively, actually, and this is how Arkani Ahmad et al. Found these polytopes before mathematicians jumped onto this, is that intuitively what these constraints do is freeze all those Mandelstams which never occur as poles in the phi cube amplitude. Because if mod I minus j is greater than 2, for example, if you have S13, then in a planar phi cube amplitude, you'll never have a pole which is 1 by S13. And that's why that motivated ABHY to find these constraints, and later they were formalized by mathematicians. So this basically locates for you the associahedron and in general any accordiahedron in the positive region of kinematic space. So now we have these forms in kinematic space, and now we have this convex, for example, say associahedron kinematic space. And okay, now what can we do? I mean, can we construct amplitudes from them? And now we are almost done. So for example, you can show that if you start with this n-3 form that we have started with, which was a unique form because it was given by associahedra, and associahedra are unique in any dimension. Then you take this form and you restrict it or you project it onto this convexly realized associahedron Kn plus. I denote both the combinatorial and the convex realization as An just because, just for simplicity. So you take the convex realization and just project the form onto this. And you can see that what you get is some form, this is not very important for us, some dx1, 3, multiplied by the amplitude. That's it. So the amplitude kind of, the color amplitude of phi cube theory just kind of dropped out. Sorry, one thing I just want to mention is that even though there is a unique combinatorial associahedra, we see that this procedure gives us many convex realization because the procedure depends on which t you started with. So for different t's, you get different realizations. So you may worry that, okay, then which one produces the right amplitude? but this is in some sense a gauge, choice of gauge. This result is independent of which realization you work with. So for any realization of associahedron, you always get this result. So you just get the amplitude. The form projected onto the associahedron gives you amplitude. In fact, this is not very surprising as mathematicians know, because associahedron is a positive geometry, and as I kind of alluded to above, that every positive geometry has a unique top form, canonical top form. And this form is actually precisely that top form on the kinematic associahedron. So, okay, so the top form on the associahedron is the amplitude of the phi cube theory. And this way of understanding the amplitude also has an interesting corollary, which actually has deeper implications. We can think of now this amplitude as a volume of a dual polytope. I mean, this is, sorry, I don't have time to go into the quantitative detail, but if you take this associahedra, which is convex polytope, you can draw like what is known as a dual. Basically, for every edge of the associahedron, you draw a vertex, and for every vertex, you draw a face. And this amplitude is nothing but the volume of this dual polytope. And this actually explains the idea of recursion conceptually, because you know that if amplitude is a volume, and we can build volumes out of volumes of smaller pieces. So we can decompose a polytope into smaller pieces and compute volume. And this is what, in fact, before any of this began, this observation was done by Hodges in the context of MHV amplitude, that MHV Young-Mills amplitude could be thought of as volumes of some polytopes in, but it was not in the kinematic space, it was in a twistor space, in a more auxiliary space. So now let me give you another example, and so this was so this was for phi cube amplitude, and maybe I can stop here and see if there is any question. Okay, then let me now tell you how to get amplitude for any other theory, any phi to the p interaction. So more specifically, let's look at phi to the 4 interaction, and a simplest example, let's take 6-point scattering. So as we know, there are we saw that there were 3 projective forms, because there are 3 possible accordiahedra for each choice of quadrangulation. Now you take these forms, and now you restrict it to the same associahedron. So you take the A6, the associahedron for 6 particles, and they restrict the form to this associahedron. And you see that naturally you get the partial contribution to the phi 4 amplitude. So if you take this omega 1,4, let me just go back. It was this one. And if you project it onto the associahedron, then you get this 1 by x14 plus 1 by x36. And similarly for the other 2, you get these other channels. Now from here, you can check immediately that you know that the actual 6-point amplitude, planar amplitude, is a kind of a weighted sum over the 3 contributions of these projected forms, where each weight is half, because you've counted each channel twice here in the form. And one can prove it. This is what we proved, that with Sujoy, Anish, Brunmay, Pinaki, and Ranjan, that this result is valid for any endpoint amplitude in phi 4 theory. That any endpoint amplitude can be obtained by taking the projective forms, restricting them to the associahedra, and then taking a weighted sum over it. So in that sense, associahedron is like a master polytope, and every projective form of different rank, like the top form gave us phi cube amplitude, lower forms can give us amplitudes for different theories. So projectivity and associahedra kind of generate these 3-level amplitudes for any scalar field theory. But okay, there is a subtlety with for everything beyond the phi cube theory, that the complete amplitude is not determined by a single polytope, single accordiahedra, but by summing over all the polytopes, like summing over all q's in a given dimension. And they depend on the specific weight factors. And you might worry, and we did worry for a long time, that if the weight factors themselves don't come from the combinatorics of this positive geometry, then one is kind of losing the premise completely. But it turned out in a remarkable couple of papers by Prashant and Ryota Kojima, they showed that these weights are actually determined from the combinatorics of the polytope itself. And the way you could determine them depends on this key property of all accordiahedras, whether it's associated or anything else, that any boundary or any face of the accordiahedra is always a product of the lower dimensional accordiahedra of the same type. So this property that I kind of referred to above for associahedron is actually true for any accordiahedron that is responsible for determination of weights. So the whole 3-level amplitude kind of comes from principle of projectivity and just looking at these polytopes which are staring at us from the kinematic space. Okay, I just end this 3-level section with a brief remark that you may have noticed that although I convexly realize associahedra in the kinematic space, I only used the other accordiahedra combinatorially. I didn't care about actually realizing them as polytopes. And you may ask, I mean, if that can be done, and yes, it can be done, although we don't need it to compute the amplitude. Just as in the case of this kinematic space or ABHY associated, any combinatorial accordiahedra can be realized in the positive region of kinematic space. And this is the work of mathematicians. And again, the same structure actually remains true. This omega q, if you restrict onto these convex polytopes, then they are really canonical top forms on this positive geometry. So everything is kind of fits together very nicely. And also we can think of them as volumes of the dual polytopes of this accordiahedra. Once we realize this accordiahedra as convex polytope, then the interpretation of this amplitude volume also become very, very clear for any theory. Okay, so maybe I just summarize the tree level stuff. So for any phi to the p interaction, there is a set of projective planar scattering forms in kinematic space, and they are just fixed by they are fixed by two requirements. One is that we want simple poles only, and the other is that we have this class of combinatorial polytopes called accordiahedra, which are naturally just there for us. When they are just there in the abstract space, combinatorial space. For p equal to 3, the form is unique, but for p greater than 3, these projective forms are labeled by this accordiahedra ACQ. And okay, but in the end, we can obtain, when we restrict these forms to the association, we produce the amplitude for phi to the p theory. And again, I don't have because of lack of time, but it turns out that all this, you may wonder why we got a local and unitary amplitude, because we didn't put anything which says that it should be local and unitary in some sense. But this really happens due to remarkable property of all these accordiahedra, that their faces always belong to the same family of polytopes. And now I will try to argue that the same picture more or less holds even for one loop integrands in the case of scattering amplitude. But maybe I can stop for questions.
Cholo, can I ask another naive question?
Yeah.
So if I start off with a massive theory,
yes.
and I take the high energy limit of that theory,
yes.
would the same structures emerge?
Yeah, actually, even for massive theory for tree level amplitudes, if you have a single mass, then what happens is that these polytopes just get shifted in the kinematic space. So you see that these polytopes are right now in the positive region of kinematic space, and they have boundaries at xij equal to 0. Mm-hmm. So if you have a massive theory, then the whole polytope get like rigidly shifted so that the boundaries sit at roughly, at m square, like m square locations. So I just didn't have time, but for a single mass, one can just easily generalize what I said, at least for even without boosting, also without going to high energy limit, even at finite energy, we have a polytope interpretation.
Okay, and you were making a statement about this special projective property that this form has. Yeah. And you were saying that it was motivated by seeing what happens for n equal to 4. And then the question was whether it happens more generally. So what is the answer to that? So what do you know for which theories do these work?
Right. So far that's a very good point. So the projective form itself is only working for massless theories so far. So the form that we write for massive theory, that won't be projective. Mm-hmm. But so I don't know what is the fundamental principle which defines. I mean, we can write the forms, we can compute amplitude, but I don't know. That is because we know the answer for those theories. I don't know what is the fundamental principle for massive theories that dictates those forms. But for any massless theories, right now it looks like the forms that we are able to construct are always projective, including Yang-Mills theory. Although in Yang-Mills theory, these forms are not sitting in the kinematic space that I am discussing here, but in the spinor helicity space. So projectivity seems like a very generic property of this, at least for massless amplitudes.
Okay.
Yeah. Okay. So, okay, Shubha, how much time I have?
You can take another 5 minutes if you want, because the last talk went kind of over time. So you
okay, thank you. Okay, yeah. So let me. So I will try to go a bit fast in the one loop case, but at least let me summarize the brief ideas that the work is based on. So here the point is that now the kinematic space that we work with obviously will not work, because we have loop variables now. We have loop momenta, so we have to introduce new variables in the kinematic space. So we have to start with, and I will explain it in the next slide, some sort of an abstract kinematic space for one loop amplitude, which I will just denote as K and L. And then everything rather remarkably goes through that. If you ask for projective forms, which have simple poles again, then it turns out that there is in fact, there's a unique projective N form, which is determined again by a combinatorial polytope, which is now a general, like you can think of it as a one loop generalization of the associated, and it's called a type D cluster polytope. And these are polytopes, again, very well known to mathematicians, but this fact was realized by Arkani, Ahmad, Hay, Salvatori, and Thomas recently, last year actually, that that the same principle that we used in tree level amplitudes seem to go through. And again, these are combinatorial polytopes, just like how we started in the associated case, but we can realize them as convex polytopes once again in the positive region of this one loop kinematic space. One realization was given by Arkani, Ahmad, and others, and then Brunmei and I found all possible other realizations of these polytopes. And then the same ideas kind of start going through that. If you restrict this form to any of the convex realization of this cluster polytope, then you get the one loop integrand for phi cube amplitude. And now, okay, this is the top form on this polytope, and you can ask what about lower projective forms? And it turns out that once again, there are unique, for example, unique projective n/2 form on the kinematic space, which are determined not by the cluster polytope, but by like a new class of combinatorial polytopes that we just called pseudo accordiahedra. And so these are one loop generalization of the accordiahedra. And again, if you take these forms and restrict to the cluster polytope, you get integrand for phi 4 theory, or in general any phi to the p theory. So it's really the same structure, but now everything is happening in this one loop abstract kinematic space. So let me just try to explain what this space is very fast. So of course we would expect the kinematic space to be bigger than the planar kinematic space because we need loop momenta. So intuitively we have to account for loop and okay, at the level of integrand also tedpole propagators. Now notice that, so one way to motivate this kinematic space is the following, that at tree level we saw that the kinematic space was coordinatized by dissections of an n-gon. So xij's could be thought of as internal chords of an n-gon. So at one loop, the same idea motivates us to look at dissections of as I will explain in the next slide, a 2n-gon with a hole in the center. So let me just quickly explain, and I apologize in advance for my crappy figure. So let me just recall for the tree level amplitude what we did. So if we have if you wanted to look at a 4-particle amplitude, then we saw that the xij's were just x14 and x13 and x24, which are dissections of the foregone. And of course, they are dual to Feynman diagrams, like these two Feynman diagrams. So this observation motivates for us that, for example, suppose I'm looking at a one loop 2-point function in phi cube theory. So I have three, at the level of integrand, I have three possible diagrams, 2 tedpoles and one a loop correction to the propagator. And then I can ask in the same way that how can I fit this Feynman diagram in a polygon? And the simplest way to do it is to look at like a polygon with 4 vertices if you have 2 particles. So like 1, 2, I'm sorry, this is too light. 1, 2, 1 bar, 2 bar. And then we can show that all these diagrams exactly in this way can be embedded into this doubled gon. And so once we have this observation, we can now ask, what are all possible internal chords of this doubled gon? Just like here, all the internal chords are x13 and x24. So all the internal chords of this doubled gon will basically be the abstract kinematic space for us now. So that will be the basis of the abstract kinematic space. So here's a slightly better figure that if you are looking at 3-particle amplitude, one loop 3-particle amplitude, then all possible internal chords are x13, x21 tilde or x2 tilde 1, x32 tilde, and all the arcs which go from say for example 1 to either the right side or the left side of this annulus, which we denote as y and y tilde. So these are the kind of loop variables. They are analog of loop propagators, and these x's are basically the planar variables that we already had. These x21 bar are a bit mysterious, but it turns out that at the end of the day, these xij tilde are really very similar to xij, except that you have to, instead of going from I to j minus 1, you have to go from j to n and all the way from n to I minus 1. So there are some combinations of external momenta. And y is an arc, again, some abstract arc right now, nothing really to do with physics, which emerges from I and touches the annulus on the left and y tilde on the right. And this was really motivated from the tree level kinematic space analysis that we did earlier. Okay, so now I just want you to recall this, that planar kinematic space is parameterized by the internal chords of the n-gon. And combinatorially, we saw that the associahedron is determined by the triangulations of the n-gon. So there were 2 things. One was that xij's were the internal chords of the n-gon, and triangulations of the n-gon gave us this abstract polytope, combinatorial polytope. Now here, in this case, we noticed that the one loop kinematic space can be understood in terms of dissections of this 2n gon with an annulus. So we can ask for the same, we can ask the same question, that can we look at, instead of like triangulations or curved triangulations, because there has to be, these arcs are curved, which are called pseudo triangulations. So can we look at pseudo triangulations of this polygon, and does it give us a combinatorial polytope? And actually, remarkably, the answer is yes. And it was shown by two mathematicians 5 years back that this kind of pseudo triangulations of this double polygon precisely generate what are called type D cluster polytopes, which were known before from this cluster algebra in the literature. So here, the pseudo triangle is just a word. Basically, what that means is that it's any curved polygon which has precisely 3 convex corners. So it can have concave corners, but it should only have 3 convex corners. So this is, any triangle is a pseudo triangle, but this is also a pseudo triangle, for example, this V2. Okay, and now just quickly I can show what these cluster polytopes are. So in a 2-dimensional case, like in this case, where we are looking at 2-point amplitude, the cluster polytope is precisely, it's just a square where each vertex is labeled by pseudo triangulations of this, of the foregon, of the double polygon. And so that's it. So that this is the analog of the associahedron. Again, combinatorial right now, we haven't realized it in the kinematic space. But once we have the combinatorial polytope, we can fix, and we demand projective forms, we can write forms again with the same logic. So we again ask in the one loop kinematic space, we write a form which has only simple poles, and where the sign of different terms is fixed by adjacency of the vertices. That's it. So it's really the same principle. And you can check this form is projective, right? That can be verified. And now, remarkably, we can do the same thing to realize these polytopes also in the kinematic space. So it's the same idea, which is, it's quite striking that it works. I mean, something that somehow mathematicians hadn't noticed before, that you say take the same, instead of working with the physical Mandelstam variables Sijs, you build Sijs out of these abstract variables Xijs that we introduce here, like these variables, and then you write these constraints, linear constraints like this. Then you can check, prove that this locates these cluster polytopes in the positive region of kinematic space. And if you restrict this form on this polytope, then you get the one loop integrand for phi cube amplitude. So that kind of completes the story for the integrand for the phi cube amplitude at least. But now this idea is so general that we can apply it to any phi to the p theory. And so generalizing the construction of the accordiahedra in the tree-level case, we showed that if you take arbitrary dissections of this hold and gone, they can be again used to construct convex combinatorial polytopes, which we just call pseudo accordiahedra. We didn't know what to call them. We just call them pseudo accordiahedra. And again, okay, I already discussed this. If you projectivity will give you a form in this one loop space, and once you take this form, projectivity and the combinatorics of the pseudo accordiahedra will give you a form. And if you restrict it onto the cluster polytope, you get the integrand for one loop amplitude. So let me just, as an example, give you one of the pseudo accordiahedra for the phi 4 theory. So if you take say 4-point amplitude in phi 4 theory, then this is one of the polytopes that you have to deal with. So it's a polytope which is labeled by these kind of dissections of the polygon, and there's a 1-to-1 correspondence between. So when we write the form, we get singularities of the form at these vertices, and the singularities are in 1-to-1 correspondence with certain Feynman diagram, which I have drawn here. Okay, I will skip this. So let me just conclude. I apologize for going over time. Although we focused on quartic interactions at one loop, we believe that everything should generalize to at least to monomial interactions for sure, but perhaps even polynomial interactions, although we haven't proved this. So in a nutshell, the principle of projectivity, or maybe more fancily dual conformal invariance, and existence of positive geometries in this kinematic space lead us to this nice restructuring of S-matrix program, where unitarity and locality kind of seem to emerge as consequences and are not fundamental postulates. And one question that we are pursuing right now is, can we, because this is all at the level of integrand. So the idea is, can we say anything about the integrals? And the first question we would like to ask is, can we classify, say, Landau singularities of amplitudes, integrated amplitudes using the geometry of these polytopes for as of n equal to 4 super Young-Mills? There has already been a lot of impressive progress in this direction by Spratlin et al. And Gurdogan et al. And this is some ongoing work with Brunmeier. I just end with this one nice result we have, that if you take all the bubble and triangle singularities many of them are spurious. Not all of them are physical singularities for massless theory. Like spurious in the sense the residues turn out to be 0, but only the physical singularities are present in these polytopes. In other words, they can all be classified in terms of some very specific boundaries of these cluster polytopes that that we discussed about. So there is some hope that we should be able to. These polytopes may be a good diagnostic for physical Landau singularities of the at least for the one loop amplitude. Okay, thanks for listening. I'll end here.
Okay, thanks, Alok, for a very nice talk, very comprehensive. We can take a couple of quick questions maybe from the audience.
I have one question.
Yeah.
Hi, Alok.
Hi.
Yeah. So the question is, I mean, suppose, we go the other way. That we want to know which kind of polytopes will generate scattering amplitude, right? What are the rules? Is there a?
Yeah.
So is there a rule that tells you that?
No. Right now, all we are seeing is that the so this one class of polytopes that we have looked at, which are coming from these dissections of polygons. And what we are seeing is that any such polytope is giving us amplitude for some scalar theory. If you take even a dissection which is very generic, like not triangulation or quadrangulation, but partly triangulation, partly quadrangulation, then you can show that will give us at least 3-level amplitude for phi cube plus phi 4 theory, for example. Now that is one class of polytopes. The other class of polytopes, there are many different classes of polytopes which not like polytopes which don't come from dissections of polygons. It's not clear which one of them give amplitude for theories. I mean, I don't know if that is what you are asking. I mean, in that sense, a spirit is like CHY. We start with some rule to build CHY integrands and see what we get. I don't know if that is what you are asking, Ashok, or
Roughly, I think that's what I'm asking.
So it's like a
the case where you get phi cube plus phi 4.
Yeah.
I mean, the relative coupling constant. So where does that enter? That's some parameter in this construction.
Yeah. So that will only enter in the form. I mean that will enter in the form, but the form will still be projective because of the fact that each form individually is projective. So you take lambda form for the lambda times phi cube plus lambda prime times phi 4. Like this is a linear combination of two forms. Each form is separately projective. So the information of coupling constant is in the form. I mean the form that we will be able to construct.
But a generic amplitude will have both powers of lambda and powers of lambda prime, right?
Yes, I agree.
And that will come out from some construction in the polytope itself. And by looking at a polytope, you will be able to say which one.
I see what you're saying. Yeah, no, I don't know if the answer to this is known. I understand now what you're asking. You're saying that suppose I just take a generic polytope with which has come from some dissection. How do I know what power of lambda and what power of lambda prime come out? That's the question, right?
That's right.
So I think naively I would think that will come from cardinality of how many of the dissections are quadrangulations and how many are triangulation. But I have to think more about this.
I see. Okay, thank you.
Okay, are there any more questions from the audience?
Yeah, Shubhu.
Yeah, please.
Can I?
Yeah, go ahead.
Hi, Alok. Very nice talk. Very nice talk. Could you indicate what happens when you have more than one field and how bosons and fermions are differentiated? Could you quickly tell?
No, we don't. Actually, there was about the fermions. I don't think, as far as I know, nothing is known. Clearly, I think that probably the right place to look at the fermion amplitude will be the spinor helicity space rather than this space of momenta. But I don't know if, to my knowledge, those that have not been investigated yet. About different fields, there is no written work, but I think that there are polytopes which are called colored associahedra. So these are polytopes which come from looking at dissections where different chords are colored in a different way. And I think at least, simple computations reveal that they may be able, they are the ones that one may have to use to obtain amplitude for say multiple phi cube different theories, as you are asking. But again, it's not like something which is a established result in the literature. That's the curious thing also. For the super young mills, of course, the form is known, but that form is in this bit of auxiliary space. It's called momentum twistor space. So here, if you take QED, then it is an open question where is there first of all even a form, even forgetting the positive geometry, is there a form for QED, tree-level QED amplitude, and if it is in which space? Which is it in kinematic space or spinor space?
Okay. Another quick question. I really don't know anything about it, so it may be naive. In the case of loops, when you have a hole, so there's annulus-like geometry, you still have only forms associated to lines which join two vertices. You don't have anything which starts from one vertex and goes around the hole and comes back to the same.
Oh, that's an excellent question. No, actually, yeah. So you are asking, suppose I take this line, like where my mouse is. Is that what you're asking?
Yeah, and it goes around the hole and comes back to the same vertex, or maybe it just touches there.
Yeah. So the comes back to the same vertex is duplicated by this line, because this is like you start with, this is a 2 and gone. So this is like 1, 2, 3, 4. Suppose you are looking at 4 particle amplitude. So you have 1, 2, 3, 4. Then these are like duplicates. So it's like 1 bar, 2 bar, 3 bar, 4 bar. So going back to 1 is this line.
Okay.
So it's precisely what you are saying. And yes. So there are these y variables that I introduced are associated to them. So they certainly occur so this line, we can, absolutely, you're right. We can think of this as, instead of introducing an extra vertex, just going around and coming back to 1, as you say. Okay. And that variable, that is precisely this loop variable here. I mean, in the propagator corresponding to this diagram here, that variable. So this variable is called y1, and it is basically 1 by y1 is the propagator corresponding to this diagram here. I don't know if that answers your.
Yeah, that's right.
Yeah.
Thanks. Thank you.
Okay, if there are no further questions, actually, Alok, can I ask a stupid question?
Yeah.
So this is about the comment about the massive case. So usually in phenomenological scenarios, we all start with a massless theory, and then through Yukawa, things gain mass. In such situations, can you say anything about the massive phase by starting out with some scheme? And is there any effort in this direction to derive some rules for massive theories which have been obtained? Masses have been generated by Higgsing and by the Higgs effect.
No, sure, not that I know of actually. Yeah. Okay. But I must say that is that question has not been explored even in more established but relatively new approaches. For example, CHY formalism. How to you're looking at Higgsing, right? So how to generate amplitude?
Right. You start your theory is massless to begin with, and then masses come about by Higgsing.
Yeah.
So maybe the S matrices of these are constrained by the original theory, which was massless.
Yes. No, I don't think actually there's any effort in this direction, frankly. Certainly not in this amplitude hidden program, but also in CHY. I think more is beginning to be known about how to compute amplitude of Higgs theories via recursion relation. And in fact, there is a paper coming out maybe next week by 2 students in IMSC, Saurav and Arka, who are actually explicitly talking about how to build DCFW type recursion for Higgs amplitudes. But not in this way, not from this approach.
Okay, great. So we thank Alok again for a very nice talk, and we will close this session. We can continue the discussion on Slack. So it's over to the conference organizers now, Tanay and Ayan.
Thank you very much, Shubho, for conducting this, and thanks to all speakers and participants. So see you soon at 2 p.m. in 2 hours. Bye.